My name is Georg. I have a last name. I work at the University of Sheffield. And my talk will be on algebraic semantics and verification. So what is algebraic semantics? Semantics means, in this context, that you assign meaning to programs, meaning in terms of mathematical objects. The mathematics used will be algebra, and verification means, as you all know, program correctness. And so my lectures will consist of two parts. You know, the first session and the second session. The first session is more conceptual. I will go through slides, explain mathematical concepts. And the second one will show you how you can basically do all the mathematical stuff that I've done in an interactive theorem prover, in this case, the Isabelle Hall proof assistant. And it's basically the design of a little verification tool based on Hoare logic, how you can do it with a theorem prover like Isabelle, but you know, the lessons transferred to other tools like Coq or Kleene, for example. And I sent lecture notes. I think they should be available on my website. These lecture notes, if you go to the end of my lecture notes, the first section of the intro section of my lecture notes, you will find some links. So there's, let me scroll. Oops, where is it? Ah, yes, here, sorry. So the first one is the Isabelle website, from which you can download the Isabelle tool. So if you're interested in trying out what I'm presenting here today, you can download Isabelle now or during the break, and then basically look at my I've got templates for you, which are basically missing Isabelle proofs that you can fill in. And if you are really ambitious and really keen, and you can do all these things, all the little proofs, all the little setups, and at the end of the day, you will then have your own little verification tool. So there's a GitHub link where you can find my Isabelle theories. And now I just want to show you very quickly the Isabelle whole website, which is this one. So Isabelle is developed in Munich and in Cambridge. Here you can download it, quick and easy. There's also documentation on Isabelle, more than you can ever chew, I guess. And that could get you started beyond my lectures. But now let's start with the real stuff. So, oh, whoops, what's going on? It's a strange mode. It's not what I want. How can I get out of here? So I need to do it again. All right. No, that seems to be better. Okay, good. So what I try here is to give you an introduction to the algebras that I will present, and also to Hoare logic and all these kind of things. And I assume that your background is very diverse. So I try to make everything very simple, because I think every idiot can make things difficult, but only few idiots can really do things simple, make things simple. And this is really something that has emerged over many, many years. So most of the stuff that I will present, I mean, in my lecture notes on my slides, I will not give any references to other work, but you can assume that most of the work is not mine. It's work that has been contributed by many other people, but it has somehow compiled into what you see here by myself. And before I really start, I want to ask a couple of questions. First of all, who of you has got, let's say, a solid maths background? And who knows, for example, what a lattice is? Or what a semi-ring is? Who of you has already used an interactive theorem prover, Kleene? Okay, yes. But it means also, you know, every question, half of the people did not raise their hands. So I take it easy, and please ask many questions, right? I rather go through half of my slides than basically leaving most behind. Okay. So when is a program correct? Yeah, that's the first question. So this is a famous algorithm. It's more than 2,000 years old. It's called Euclid's algorithm, right? So you know integer division. So how do you know that this algorithm is correct? Yeah, so what would you do in order to figure out whether this algorithm is correct. Hmm? Unit testing. Yeah, you're in the wrong room. You're in the wrong room. Yeah. I don't want to... Well, yeah. I mean, unit testing, you know that you test a couple of values and you know that your algorithm is correct on these values. This may be enough for many applications, but in some situations, it's not good enough, right? So we want to do more than that, yeah? So not unit testing. So now we know when a program is correct if you don't unit test it. Yeah. But then, you know, I mean, there are two kinds of questions, right? If I can maybe figure out why this program is correct, but that does not tell me yet what program correctness means in general and how I can develop a general method that allows me to prove program correctness. Yeah. So, I mean, in order to understand what program correctness is about, first of all, I mean, so that could be just some random code, and we could ask ChatGPT, you know, what this program does. And maybe, you know, it could find an answer, who knows. But for us, it would be very important as a first step to know what this program is actually meant to compute, right? And in fact, what you compute is the quotient and the remainder of the two numbers, x and y, the dividend and the divisor. And it's also clear what outcome you would get from this program. Q values q and r that satisfy this equation here. So that's namely the x is equal to q times y plus r, as we all learned at secondary school. But then if you look at the program again, you would notice, oh yeah, now it gets complicated. I need to stay here. So you would notice that already after the initialization, this equation holds, right? So that's not good enough. We need to be a little bit more precise. And in fact, we also need to require that the remainder r is strictly smaller than 0, right? So that's what you see. And how is this algorithm computed? I think when Euclid or somebody else came up with these algorithms, you know, they did not have equations. They did not know what equations were. And also they did not have proper numbers. I mean, the Greeks, they were using Greek letters, alpha, beta, gamma, for numbers. They could not even properly calculate. So how would you figure out whether the algorithm is correct? And I mean, if I had been Euclid, I think I would have used the following method. I take a piece of rope of length x, and I take another piece of rope of length y, and I put the pieces together, and then I cut. And then I count how many times I can cut my rope x, right? And that gives me q. And then, you know, when the remainder is smaller than the y that I'm trying to cut, that gives me, the q, the quotient, and the remainder is given basically by the leftover rope, right? So that's the argument. And who would doubt that this program is correct? Anyway, we need to be a little bit more careful here. So, I mean, now we know what basically the outcome of the program should be. But the next question would be, what are the admissible inputs? So which values can I accept? So here we are restricting ourselves to the natural numbers. And you can see that you can, I mean, if you think about it a little bit, that you could accept any number x as an input. For y, you can use every number except for the 0, because if we have the 0, then you see that basically our remainder never changes and the loop will run forever. Yeah, that means that the program will not terminate. And termination of the program is, of course, also an important part of correctness. So as a summary, we deem our program correct if it terminates and if its output satisfies this kind of equation or this kind of conjunction of two equations or two relations, if you want. And this is meant to hold if we execute our programs that satisfy this constraint on y, and whereas x is not constrained at all. And traditionally, people call x non-equal to y the precondition of the program, which tells you, you know, from which values you can execute it. And then this other condition that we all assertionist people say is the postcondition of a program. So more general, in program verification, people use two notions of program correctness. So the first one says that if a program that has a is decorated with a precondition P and a postcondition Q as assertions, we call it partially correct if whenever it is executed from states where the precondition holds, and assuming that the program terminates, then the program will terminate in states where the postcondition Q holds. So this P here is and then that's a weak or partial notion of correctness. The total notion of the notion of totally correctness would say that whenever our program is executed from states where the precondition holds, and if the program terminates, so you need to prove termination here instead of assuming it, then it will terminate in states where Q holds. And in fact, in practice, if you want to prove total program correctness, you can prove partial correctness and termination separately. So these are the rules of the games. Now, how do we know that the program is correct again? You know, how do we prove it, or how do we show it? So to verify the termination of the program is quite easy. So you suppose that we start from states where the precondition holds, and then you will see that this term here becomes smaller all the time, right? Then at some stage, it will become, R will be strictly below Y. Then the test of the loop becomes negative, becomes false, and the loop is no longer executed, the program terminates. And this is a notion of termination where we only care about the termination of the loops, right? So it might also be the case that, for example, a test does not evaluate or some other things happen, but this is really, these kind of things are ignored with these notions of termination. So how do we prove that the postcondition holds if we start the program in the precondition? That's the partial correctness, if you want. And that would be basically making this kind of idea of the rope cutting a little bit more formal. But that is a little bit problematic, right? So if we just say that, well, Y is subtracted from X so long as Y is smaller or equal to R, and then we count the number of subtractions and we have these leftover pieces, that's not really convincing. And it's even worse than that, because the program, if you think about it, is even correct when X is strictly smaller than Y. Because then we can initialize the program, the postcondition holds, but the loop will never be executed, right? So that's a corner case. And corner cases are usually the bad guys in verification. You know, you follow your intuition, but often there are these nasty little conditions that you don't even think about. And this is where verification often fails, right? So what do we do? So it means we really need to formalize the whole thing. We need a mathematical notion of program. We need a mathematical method that helps us in this verification, which picks up all the corner cases. And then we can really be sure that our program is correct. Okay. So, I mean, the bottleneck in program verification are, of course, the while loops, right? So as we are not doing unit testing, so we can't just say, okay, let's check the loop for 5 iterations. And if that's good enough, okay, then it will also be correct on all other iterations, right? So we have really something where we never know how many iterations there will be and when the test of the loop will become false. So that smells like an inductive argument, right? So we want to prove that basically somehow by induction on the number of loop iterations. If we have an inductive proof, we need a property, right, that we check. But what is the property, right? It's a property that needs to hold before each execution of the body of the while loop and after that, right? That would be the property P in our induction proof. And because a program in some sense is a discrete dynamic system, what we are looking for is something like an invariant of our system, right? An invariant that holds before and after each iteration of the loop. And that is called so-called loop invariant. And that is really the bottleneck of verification, because it requires in many cases creativity to find the right loop invariant. It's not something completely algorithmic. And that's why people don't like to verify programs in most cases, right? So in this example, our loop invariant would be X equals Q times Y plus R, because we have seen it already holds after the initialization. And then we need to check whether it holds when we execute the loop. What happens when we execute the loop? Well, we know that Q is incremented and Y is subtracted from R. And then we write the same equations with these values substituted. And then as we learned at primary school or wherever, we can really check very easily using arithmetic or whatever that this equation is true. Then we have an invariant. And then, of course, this is when the loop goes through in our program, but we still need to check the post condition. So essentially, we need to show that the loop invariant implies the post condition. But as we have seen, the loop invariant is the first part of the post condition, and then the second part of the post condition is just the negation of the loop, was just the negation of the test of the loop. So it will really hold, right? So this is now a semi-formal verification proof, as you would find it, for example, in this kind of common Rivers Gleiserson book on algorithms. Most of the algorithms they discuss in this book are verified in such a way. It's mathematical reasoning, and it's usually very intuitive. And for the standard algorithms, thousands of people have read it, and nobody would doubt that these programs are correct. But for verification, it's really not good enough, right? So we need to turn this verification approach into a method, that does not work just for this program, but for any program, or at least for many programs, for a large class of programs. And as I said before, we therefore need to model programs as mathematical objects. We need to formalize their correctness conditions in a mathematical language and use a mathematical language to do mathematical proofs about these programs, right? And then finally, we want to execute these proofs on a machine so that the machine can check step by step whether all of our calculations are correct. Because we trust machines more than humans, right? And that's what these lectures are about. Okay, any comments, any questions so far? Maybe I bored you? No, I don't know. Okay, so let's now move to algebra, right? So here, because we keep things simple, I will just look at a very, very simple while language, right? Where we just have assignment, sequential composition, conditionals, and loops. And you can think about a programming language called imp in some cases, where even the expressions that we have here will range over the natural numbers or something like that. Simple arithmetical statements. So this syntax defines the commands of our programming language. And even these basic commands, which are given by the assignments, we will now consider unstructured, right? So we just have some basic commands, A, B, C, D, E, F, G, or whatever you want to call them. And we will also identify programs with commands to make it easier to talk about these things. Right? So now we want to develop an algebra for these programs. And ultimately, what algebra does, reasoning about numbers in school, algebra tells us when one thing is equal to another thing. That's basically what algebra does at the bottom line. And these things that we are talking about can be presented in very, very different ways. You can write down two numbers in very complicated ways, but nevertheless, in the calculus of arithmetic, you can check whether the left-hand side of the equation is equal to the right-hand side. And we want to do basically the same thing for programs. So the first question we need to ask is, what does it mean for two programs to be equal? And that's a very, very difficult question. And there are, in fact, many, many answers to that. It depends on what properties of programs you want to check. So here in our case, when we do this verification of sequential programs, we are mainly interested into the relationship between preconditions and postconditions, which means all we care about is basically the inputs and the outputs of the program. So we use a very, very coarse equivalence on programs, which just say we deem two programs equivalent if they compute the same outputs from the same inputs, right? So if you take quicksort and merge sort, they compute the same outputs from the same inputs. These two programs are the same for us. We identify them. We don't care of what is going on, during the computation. Okay. So further assumption. So we abstract a little bit. So we allow programs to compute several outputs from any input, or no output at all. Yeah. So our programs can therefore be non-deterministic. You have these kind of branching situations. And there are two reasons why we do that. First of all, it simplifies the mathematics, in particular the definition the semantics of the while loop. And also it means that it can use specifications which may not be executable and lead to many results as particular non-deterministic programs. And then another simplification that we make is that we consider the tests that we have in conditionals and loops as special programs. And these are something like measurements or observations of the state of a program that cannot actually alter the state of a program, which is no longer true in concurrency, of course, but in the sequential world, that's nice. Yeah, it works. Okay, and now we want to develop an algebra of programs based on these kind of ideas. And that will be an abstract semantics of program equivalence, and also give us a notion of what some people call program refinement, which tells us whether one program is more deterministic than another one. And then later, we will develop a much more detailed semantics of the program store, but this is basically a unification of many of them, right? Because every abstraction needs two instances. If you have one instance for an abstraction, you can ask yourself why it is worth doing this work, right? So here we need at least two semantics that justify why we make this algebraic generalization. And then I will also show you why, what these two examples are. So in our first go, we will even ignore tests in the program, and we will generalize the conditionals that we have in our simple while language to non-deterministic choices. The while loops, they become finite, unbounded iterations. And then we add, for reasons of algebraic simplicity, we add two special programs, the program skip, which can be executed from any state and does not change the state, and the program abort, which can never be executed and also therefore never produces any kind of output. And I will simply write X, Y, Z for programs, and the equality sign will be used for program equivalence. So what kind of properties do we expect, right? So these are now design decisions, and you might object to many of them. But again, for this kind of simple program verification, it will magically turn out that these are the right ones. So let's look at the first one, sequential composition. I just write it as multiplication. So one is if it is nothing, right? If I do nothing, and after that I do something, it means that I just do something. That's the first law, right? And of course, if I do something and then nothing, I'm just lazy, then I just do the thing that I've done. That's the second law. Abort, 0. If I abort and then try to do something, I'm still in an abortive state. I cannot recover, right? That's already an assumption. You could debate it. Second one too, if I do something and then abort, I lose all the information about the thing that I've done before. Again, debatable. Associativity works because we only care about input-output relationships in programs. And of course, no programmer has ever been done for not writing brackets in sequential compositions. Right? So nobody would doubt that. Non-deterministic choice. So the order in which the choices have been laid out to me here and there do not matter, right? If I choose between X, Y, Z, I just make these choices in any kind of way I wish. That's what the first two axioms say. This is what a good friend of mine who grew up in the Soviet Union calls the Stalinist choice, right? If I can only choose between X and X, there is no choice. And then this is again something we can debate, right? So it says that if I choose between X and abort, which is the worst thing that can happen to me, right? I will always get the X. So this is what some people call an angelic choice. It says that an angel always guides me towards the good side of things, so to say, right? But again, you might debate that. Finite iteration, unbounded iteration. So what should hold is that, for example, if I do an iteration of X and do this iteration one more time, or else I do nothing, that's the same as just iterating the thing. Nobody would object, right? And you can also do it from the other side when you think that programs are going backwards in time. So I iterate my program backwards from the end, and then I keep iterating, etc., etc. But I mean, that's not quite good enough, because if you think about having an iteration that can be finite or infinite, so these two equations would still hold. So we need to be a little bit more precise, and I'll present that later. And then finally, we have interaction laws, which are called distributivity laws. So the first one says that if I choose between X and Y, and then afterwards I do my Z, I need to be able to do Z after my choice of X and my choice of Y. So I guess everybody would be happy with that. Yeah. This one is again more debatable. So this says, if I do my X, then afterwards I choose between Y and Z. That's the same thing as doing X followed by Y, or in the other choice, X followed by Z. Right? And that works again because I only care about the input-output behavior of programs. If you say, no, I want to be more precise and I want to memorize the point at which choices are made, then I can't have this equality. So for example, some of you might know about process algebras. People in process algebra, they would say, no, you can't write this. We can. Okay. Yeah, but of course, this is all hand waving. It's an intuition. We need precise semantics to back this kind of stuff up. Any questions about these assumptions or any comments? Yes?
I don't really understand the iteration.
The iteration line. Well, it says that if I so this says basically you do X a number of times, including 0 times. If you do X 0 times, you just stay in the state where you are, which means that you skip. And otherwise, what you're doing is you're just unfolding your loop once, and then you keep iterating. Yeah. So the plus is a choice is like an OR. Yeah, and it's a choice because we have this, it's not like addition of numbers, it's because of this kind of Stalinist idempotency law that turns it into a choice. Any other questions?
The ... in the finite iteration.
Oh yeah, I will come to that. Okay, now what we are doing is that we are basically packaging this kind of intuition as mathematical structures, right? And first, we just define an algebra of program that basically satisfies the law for our sequential composition, the choice, the skip, the abort, the skip, and this kind of finite iteration. And this assembly is also reflected in the way how we are setting these things up with Isabelle. So the first thing that we have is a monoid, right? And who does not know what a monoid is? Okay, yeah, so I say it very quickly. A monoid is just a set where you have an operation, which is a multiplication, which is associative, and you have a unit element, which is a left and a right identity with regards. These are precisely the laws that you saw in the first line or something like that 2 slides ago. There's nothing but that. Monoids are maybe the most fundamental structures that you can encounter in computer science, except maybe for categories. And yeah, there are other examples of monoids. I mean, I've written them down. I do not really want to discuss them here. You can stare at them while I'm talking, but we really need the fact that sequential composition satisfies the laws of a monoid. Yes, and then a monoid can be commutative, and that means basically you can swap these 2 arguments. Sequential composition of programs is not commutative. Matrix multiplication is not commutative. Addition of multiplication of numbers, of course, is. So the next thing that we consider is a semilattice. A semilattice is a commutative monoid in which we also have idempotency. I write now because it's commutative addition and use the 0 because these are the natural things to use in an additive setting. So now we have the law x plus x is equal to x. That's just the formal definition. But if you remember what I wrote down as the laws that are satisfied by choice, it's precisely associativity, commutativity, and idempotency of plus. So these are the 3 laws that need to hold. Right. So there are other examples, and that's very important. If you take the set of a set, the so-called power set of a set, and then you consider the operations of union and the empty set on that structure, that will give you semilattice. So semilattices are interesting because you can define an order on them. So for example, if you have sets, you know that one set is contained in another set if the union of the first set with the second set equals the second set. You can draw Venn diagrams if you don't believe them. And we can write precisely this same equation or equivalence abstractly for semilattices And we can check that this relation is a partial order relation. So it's reflexive, transitive, and anti-symmetric. And in our program context, it means basically this inequality holds if this program is more deterministic than that, right? It's some sort of refinement order. I think people in the refinement community usually use the reverse order, but I think refinement has pretty much been invented in the UK. And as everybody knows, the people in the UK also drive on the wrong side of the road. So here are some interesting laws of semi-lattices with regards to the ordering. So 0 is the smallest. So aborted the program is the worst thing with respect to this ordering, if you want. Then you have some order preservation properties. And then you have, for example, this property, which says that x is below x, the choice of x and y. So which means that x plus y is an upper bound of x, and because of that law, also of y. And then this law says that basically the x plus y is the least upper bound of x and y. Yeah, and the least upper bound is called the supremum as well, or simply sub. So you can take that as an alternative definition of semilattices. You can just say the semilattice is a partially ordered set in which each pair of elements have a supremum, a sub, right? And so you have basically, for lattices, you have this kind of algebraic view on the structure, which is given by the 3 equations that I gave, and this kind of order theoretic view. And that's important in program verification. Okay, now we plug these 2 things together. So we now define a structure where we have the multiplication, the addition, the 0, and the 1. And that gives us a semi-ring if we impose these two distributivity laws, plus the 0 laws that we have already seen on my previous slides. And we call it dioid, a semi-ring in which the addition is also equal. So x plus x is equal to x. So what we have now seen is that dioids model programs with sequential composition, non-deterministic choice, skip and abort. And also we have order preservation laws, which means if x is below y, then I can always pre or post multiply with the other element set, and it will still be in this order relation. So now the only thing that we need to consider is the star. Yes, I've got further examples, matrices, for instance, but let's not go into details. So there's the only thing that is now missing is the Kleene star, but first of all, which models the finite iteration. But first of all, let me mention an important concept, which is opposition. Opposition means that I stop the order of multiplication. And if you had all the laws that I gave you so far on one slide, you will see that semirings and dioids are closed under opposition. If I reverse multiplication everywhere, I would get other laws that hold in these kind of semirings or dioids. And this is a property that therefore saves us a lot of work in proofs, because you do half of the proofs and then you can always say the rest holds by opposition. It's a duality, if you want to call it like that. Okay, and finally, that's now the slide with the iteration. Now we come to these so-called Kleene algebras, which are, so far everything has been pretty traditional for mathematicians, except for the idempotency of plus. But here it gets a little bit weird, right? Because now we have the iteration, which does not really feature in mathematics, but it can also be axiomatized in an algebraic way. So first of all, our good friends, the iteration laws that we have already discussed as inequalities, but you can also derive the remaining part. I could have written equalities here. But I said these laws, they also hold for possibly infinite iterations. So what people came up with is 2 more laws, right? And that also answers your questions. These are the dots that we had. And what does this say? Suppose that z is 1, right? Then we see that 1 plus x times y is below y, which is basically this inequality with the x star replaced by z. And then here we will see x star is below y. So what it means is that suppose we have another z, another element z that satisfies this equation for the x star, then the x star is below that y, which means that the x star is the least element that satisfies this equation. And then these equations here down there, they are just the opposites. We don't need to worry. We need them, but we don't need to worry about them. Yeah. So That means essentially that the iteration is the least element which satisfies the iteration, as I said, and that distinguishes the finite iteration, finite unbounded iteration, from possibly infinite iterations. So here we need to generalize from 1 to z, but for reasons I do not want to discuss that. From a pragmatic point of view, I would only want to say if we had a 1 here instead of a z and everywhere else, we could not really prove the properties that we want to prove. For those of you who know about that, it says basically that the x star is the least fixed point simultaneously of the following two functions. So now Kleene algebras give us a model of programs with sequential composition, non-deterministic choice, finite unbounded iterations, skip and abort. And because Kleene algebras are so exotic, I want to add a couple of more comments about them. So for the people who have training in computer science, I want to mention that regular languages over an alphabet sigma form Kleene algebras. Right? So for the mathematicians here, I would say if you do a power set lifting of any monoid, where the multiplication at the power set level becomes a power set, becomes a complex product, you would obtain a Kleene algebra. If you are more categorically minded or like graphs, and you have an algebra of parts in a directed graph where you can glue parts together on their ends if they match, then you can show that if you consider sets of parts and equip that with the right kind of operations, you get another Kleene. So every category, in some sense, or every directed graph generates a Kleene algebra. Matrices form Kleene algebras if the coefficients are chosen in the right way. So if you have matrices in which the coefficients come from a Kleene algebra, you get another Kleene algebra. And the definition of the star is a little bit more complicated, but you can use these matrices essentially to represent finite automata. And yeah, anyway, I mean, there are lots of applications for these exotic structures, and it's not something that just pops up in the context of program verification. It's studied by a small but slightly wider community in theoretical computer science. Any questions up to now? Here are lots of properties. So those of you who have done formal language theory might recognize almost all of them from language theory, because they are all equations that you would expect to hold of regular. I do not want to go into detail, but this is something that you can practice with Isabelle. If you want to do non-trivial proofs with Isabelle, all these lemmas are in my templates, and you can fiddle around and try to prove them. Okay. So here's just an example how you would do a typical proof in Isabelle. And here, of course, by hand. So let's prove the following fact. If I have a finite iteration, and then I do this finite iteration again, then the second iteration is a complete waste of time, right? That's what this lemma says. I just need to iterate once. In order to prove that, the typical rule of thumb that you do on, let's say, proof recipe in a Kleene algebra, to try to prove it order theoretically, because the working horse of Kleene algebra are these two induction laws. You often need these, and here you have proper inequalities, right? So that's always a good way of approaching that such problems. So you split into two inequalities, and then as you see here, you have a property. And then you apply star induction, and then you need to prove a simpler property in which essentially this star here has been replaced by this here. And now, because the plus is such, you can reduce that to inequalities between this term and that one, and this term and that one. This is completely trivial. It holds just by reflexivity of the partial order relation. And this follows again by properties of sub, because of this axiom. This, right, if the sum of this is below x, then in particular this element must be below the x. then this is the other direction. And this is even easier, right? So we know that if star, I can right multiply with a 1. And then I know that 1 is below x star. Again, because of the property that we had here. Right? So we know 1 is below x star. And then, I can finish my proof. Right? So x star is above x star. Okay, and then anti-symmetry of by order relation gives you that. Why do I show you this proof? 2 reasons. First of all, because I want to bore you. And second reason, because you can maybe imagine that executing such simple equational proof steps is very easy for any automated theorem prover. Right? So nice thing about this algebraic reasoning is here, you just give it to an automated theorem prover and you wait, you have a coffee if the proof is a bit harder. And then you go back, it's quite likely that you get a solution, that you get a proof, right? So this kind of algebraic reason is very easy to automate. Okay, this I skip. So the next ingredient, because I want to bring you closer to programs, the next ingredient are Boolean algebras, right? So here I don't ask whether you know Boolean. Was there a question or were you just lifting your arm? You. Okay, sorry for asking. So Boolean algebras, here I don't ask who knows Boolean algebra. I simply need to assume that you know what Boolean algebras are, right? But they fit with similarities. Boolean algebras, I have inf, I have sub, I have a complement, I have the and the greatest element. And it's basically formed by 2 semilattices. For the inf operation, one for the sub operation. Then I have some laws between them, which are called here distributivity laws and absorption laws. And then I have a complementation, which basically satisfies the operations that you know from logic. So that would correspond to excluded law of extreme middle. And an important example of a Boolean algebra would again be the set of all subsets of a set with the operations of intersection union, the empty set, the whole set, and then the essentially the set minus or the set complement that we have. Okay, now we want to get away from this kind of finite iteration and choice business, and we really want to talk about conditionals and while loops. So what people have proposed, actually, it goes back to ideas of Ernest Marnus, a famous category theorist, and then later Dexter-Colson. A Kleene algebra with tests. Kleene algebra is now a Kleene algebra, where you have a second set which forms a Boolean algebra, and then you have these shared operations, multiplication, addition, 0, 1, and star, and then you have this complementation operation that lives only in the Boolean algebra. So that means that multiplication plus 0 and star form a Kleene algebra. Multiplication plus minus 0 and 1 form a Boolean algebra, where the multiplication, the Boolean algebra is the sub, and the plus in the Boolean algebra is the inf operation. And we require that this is a subalgebra of K. So if K is our big algebra, we have our 0 here, we have our 1 in the Kleene algebra. And this is basically the direction of the order. Then the Boolean algebra lives in this lower part between the 0 and 1 of the Kleene. So the operations in this context have 2 purposes. So on the one hand, multiplication and plus are sequential composition and non-deterministic choice in the big algebra. And restricted to the small Boolean algebra, the multiplication and the addition become sub and inf, as I already said. And we call these Boolean algebra the algebra of tests of the Kleene algebra, right? And also 1 and 0, they are brought and skipped in our Kleene algebra, and they represent false and true in our Boolean algebra. That's the way it's done. And the intuition is basically what I said before, because the Boolean algebra is a part of the Kleene algebra. It means essentially that the elements of the Boolean algebra, the tests, they will correspond to programs that can observe or measure properties of states, but they cannot change them. That's the idea. So, and then just to give notation, so I will write PQR for tests, and I will continue to write XYZ and so on for programs. Any questions about Kleene algebra with test? Okay. Good. So now, just to give you some intuition about it, when you multiply a test with a program, so the intuition would be that P represents like a test in a program, a predicate or a subset, a set or something like that, right? And if I write Px, that means that our program X will be restricted in its input to states that satisfy the property P. That's how you should think about it. And if I write Xq, that means I restrict my programs in its outputs to states which satisfy the property. That's what it is. And then there are a couple of identities that will be equivalent in any case, which is again a nice exercise to do with Isabelle, but it's not strictly needed. I just want to emphasize that these properties are important, and they are nice little exercises needed still at this point. Okay, now after all this build-up, we can now give a semantics for conditionals and while loops in these Kleene algebra tests, right? So the conditionals, remember before we had just non-deterministic choice, and instead of a while loop, we just had this unbounded finite iteration. So now in this case, we have a Kleene algebra with tests. We can say, okay, what does a conditional mean? If the test is true, do X. If the conditional is false, if the test is false, then go into the Y branch of the program, right? So choose between Px and non-Py, but the choice is no longer a real choice because the choice is really triggered by our predicate being true or false, yeah? And that gives us an algebraic, so if P, then X is Y. Any objections? No? Now the while loop. So what does the while loop say? The while loop says, so long as the test is true, keep iterating your while loop, right? So check whether the property P holds. If that's the case, execute your X, check it again and again and again and again. And then if the loop stops, you will find yourself in a state where the test P must be false, right? So that's basically Kleene semantics of the while loop. Any objections about that?
Always infinite iteration.
Well, I mean, maybe you have already seen secretly my next slide. I'm just, or maybe we have written some papers together on this. Who knows? Yes. No. Yes, previous page.
Have intention X, and we said that it can be like a predicate of yes.
Yes.
And you have XP as well. It means that chance.
No. Here, for example, it does not mean that I can change would be. No, okay, I tell you what that means. It means that, it's good that you say it now because then I don't explain it later. I would have explained it later. I explain it now. So this means basically, if I execute a program, suppose P is a precondition and Q is a postcondition in the context of verification. So that means whenever I execute my program from states where the precondition holds, then I'm safe because I know that I will find myself in the set of states where basically in the situation where my program is executed into states where the postcondition Q holds. Which means, so whenever I execute first P and then X, so I know that afterwards Q will hold because of that relation. And that also expresses it in a different way. So this says, if I execute my program from states where the P condition holds, then it's impossible that I end up in states where the postcondition is false. This is how to read these properties. Yeah, thank you for asking. I think maybe I should have explained that. Good.
I wouldn't have ever really explained it.
No, this is the best way.
Just PNS needing to execute. We said that there's a ZX that would also need to execute. ZX is aimed, then that will be. So what you're saying is XQ is VeTSS from P, get PXQ. But there's also ZXQ. That basically exists XQ.
I don't need a Z. I mean, so the way,
That's why the less.
I know, but the way the order is defined is this case if px plus xq is equal to xq, right? So I don't need a Z. It's equivalent what you say. I mean, you could say there exists a Z, but it means basically, I mean, if you say there exists a Z, that means basically if I add to this something else, then I will be as good as xq, right? But the thing, but in the context of these semi-lattices, this Z is basically given by the xq. Yeah. No, but you are absolutely right. Yeah. So, I mean, sometimes people say, so while loop means can be specified as follows. You can say while loop means that if P holds, then you execute your loop once, and then you do your while loop again, right? And if P does not hold, then you just skip and you do nothing, right? And this is now something you can prove in 3 or 4 steps using the laws of Kleene algebra with Hess. And in fact, you can even show that the while loop is the least fixed point of basically the function that I have written up here if you replace the while loop by an X. And the proofs are very simple equation proofs. Again, they can be done by theorem provers. Right? So this, I show this because it's an example of a proof transformation. Right? So you can say, some idiot has written a complicated program, and now you can prove with Kleene algebra with cut, basically, that it's just a simple while loop. Yeah. So here's another example of a program transformation. No, now we come to Bridges. Now we come to Bridges' question. So how do we do infinite while loops, right? So, I mean, certainly the idea would be an infinite loop is a loop where the test is always true. Yeah, so you write your while loop like that, while one do X, okay? Then you go back to the semantics of the while loop, and you notice that there's this non-P at the end, right? So you need basically, if the test is 1, at the end you need to multiply with the 0, which is this, right? So you keep iterating X, and then 0 strikes. But because 0 is an annihilator, the whole thing becomes false, right? So that's not an infinite loop. Which means that it, you know, what we said, what I never said, but we just asked for, cut is really an algebraic semantics for partial program correctness. It does not allow you to reason about infinite loops. If you want to reason about programs that may not terminate, you need to slightly change the axioms. I mean, there are some axioms that go away, but I do not go into details. Yes, here's another program transformation, right? So just an example. So if you have this kind of, that's now a proper commutativity condition, right? It's like in classical mechanics, you machine measurements, then you do something, property still holds or something like that, right? And so it means basically it doesn't, so basically the test that you perform does not depend on the program, or the program does not depend on X. So independency in program analysis are usually commutativity conditions, right? So, and that means if you have such a condition, then you can pull the test into the while loop. And again, you know, it's just a simple calculation. So if you pull it into the loop, you need also this property here, because you need to push it into the negative and the positive branch. But this is basically provable. I do not want to explain how, just to show you that it's not too hard. Theorem provers can find it, and theorem provers can find it. Yeah. And one of the early success stories of Kleene algebra with tests, in fact, has been that people showed a very kind of well-known theorem that nobody really could prove in an easy way, which is the so-called folk theorem about while loops. And it says whenever you have nested while loops, if you add auxiliary variables, you can replace it by one single loop. Yeah. And people did it by various means, and you know the proofs were long and horrible. And Dexter Kosenberg, he gave a proof in Kleene algebra, which you cannot really automate. You can't just type it into a prover and then prover will say yes, it's true. but at least it's, if you do it in Isabelle, it will cover something like 1 or 2 pages. And that's one thing that cut is good for proving these kind of little program equivalences. Okay, so that was basically what I wanted to say about the algebraic semantics. So you have this Kleene algebra, and that in one way or another models simple while programs. Okay. So the next thing I want to move to is semantics that are more concrete and give us a more detailed view on program executions. And because I said that every abstraction requires at least 2 instances, I give you 2 more concrete semantics of programs. One is the relational semantics, and another thing is that computer scientists call the state transformer semantics. Both will be models of cut, which means that all the laws of cut will hold in these semantics. So, and that is quite useful later. And then, of course, to verify proper programs, we still need a model of the programs. So the first model is given by binary relations. Who of you does not know how binary relations work? Everybody knows about binary. That's good. That's good news, right? So just recall that a binary relation on a set X is just a subset of the Cartesian product. So the elements of relations are ordered pairs, and I will just write a rel X for the set of all binary relations on the set X. For us, important is that in program semantics, so this AB, these kind of pairs, they give us just, the relationship between the pre and the post conditions of our program, the input states and the output states, I should say. And unlike functions, of course, relations support non-determinism. So I can have the B and the C relate to the same. But I think we all learned that in primary school. Okay. Binary relations, of course, are sets, and therefore they form Boolean algebras. So they even form complete atomic Boolean algebras, if you want to be precise. So the empty relation is basically the bottom element of the Boolean algebra. The universal relation, which is just the Cartesian product, is the top relation. And then you have union and intersections as sub and infs. And then you also have this Boolean complement, which is basically set minus with respect to the universal relation. And that gives us already enough to talk about non-deterministic choices and abort and our refinement order in this setting. But relations have 2 more important operations. The first one is the relational product, right? It says that with my relational product RS, I can go from A to B. If I can go from A with R to intermediate state C, from that state to B. And the identity relation is basically something like the diagonal relation. So the pairs all A, comma A, such that A is in the set. Now, we have basically everything now except for the finite iteration operation. In the relational semantics, it will just be the reflexive transitive closure. Yeah. So it can be defined inductively so that you can feed it into a theorem prover. R to the 0 is just the identity relation, which will be skipped basically in our relations. And then that's basically what you expect. And then here you take the here. Yeah, that's how the reflexive transitive closure can be. And that really shows you that we are really talking about a finite unbounded iteration, because we know that the pair AB is in our star if and only if there's a natural number I such that A, comma B is in R TBI, right? It's finite and it's unbounded because we do not know what the R is. Right, so what we now want to show step by step is that relations form a TBI. And I will show you some of the steps because these are things that you can later do in Isabelle, if you wish. So first we should show that we have this dioid structure, which means that relational composition and the identity relation gives us a monoid. Then the union, the empty relation give us a semilattice. And then if we pull them together, we have distributivity laws that we need to prove, and we have the zero. This is very routine. There's nothing really difficult about it. And I just show you proof as an example, right? So in order to show that ST is equal to RST with the brackets rearranged, associativity of relational composition. So you know that two sets are equal, even though if they have the same element. So suppose you have an element here, you need to show that this is the case, even though if you have an element on the other side. And what you're doing is that you're just expanding the definitions of relational composition. And then here in the middle somewhere, you are using the fact that you can swap quantifiers around and that a logical end is associative. That basically gives you the proof. So then in the next step, in order to show that we have a Kleene algebra, it's worth verifying that we also have infinite distributivity laws. So where we have now a set, so this calligraphic S is a set of relations. And then we have this kind of distributivity property here. And again, it's just unfolding definitions and using here the fact that if a pair CB is in this union, then it must be in one of the relations that can be found. It's very simple set theory if you want. And that can no longer be done, for example, by first order theorem provers, because now we are reasoning about sets and so on and so forth, maybe. But it can still easily be done with interactive theorem provers. And after showing that, we can now show that we get Kleene algebras, right? For the Kleene algebras, this is basically one of these laws that we had, one of the axes of Kleene algebra. And the way it is proved is we know that the identity relation is R to the 0. Then we have this R times R star. So we unfold the definition of the R star. And then because of the law that we have proved before, we can now pull the R into that union. And then we know that now here we are reasoning essentially over powers starting from 1 instead of 0, and the 0 is given here. So if we reassemble that, we get the star back. And then for the induction laws, we show by induction that's basically Ri. So we assume that T union R composed with S is below S. And then we show that we get R to the I composed with T is below S. And using that, we can then prove the property of the star. And that's a simple induction on the I. And again, these are things that you can easily do with interactive theorem provers. And then if we want to go from there to cut, we need to decide what tests should be in this kind of setting. Right? And these in the relational setting are so-called sub-identity relations that are relations that live between the identity relation and the empty relation, which means that each sub-identities relates some elements of X with itself and maybe some elements with nothing. Right? So that's the definition of a relational sub-identity. And intuitively, you can view them as subsets, or you can view them as predicates. And I decide to write rel 0x set of sub-identities. Not want to explain. And I will write P and Q for relational sub-identities, and I can define a complement on these sub-identities as the relative complement of P with regard to the identity relation, so that it really lives, that the complement also lives below the identity relation. And after that, you can prove your main theorem about the semantics. It means that the structure that we have set up in the way you have just seen, our relations over X, the sub-identity relations over X, sequential relational composition, union of relations, the complement, the empty set, the identity relation, and the reflexive transitive closure operation, they form a Kleene algebra. So now we have basically a relational model where we can see program executions going basically from pre-states to post-states in a program. Yeah, and also the remaining bits that the subalgebra, that the identity relations form the subalgebra, etc., is routine and can be carried out with a proof assistant quite easily. That's the first semantics. And the second semantics for some people will be more obscure, but for other people it will be maybe even clearer. So who of you know about functional programming, monads, and categories? Okay, then I will throw in maybe some remarks about that. Okay. State transformers, that's an alternative view to relations. Instead of considering binary relations, consider non-deterministic functions. These non-deterministic functions map one element to a set of elements. That's what it is, right? So you can go from one element maybe to the empty set, right? Which means that you cannot execute from that element. You can go to one element like you could do with a function. But if you go to two or more elements, it's like executing a relation. Yeah. And I will write star for statements on the set of all state transformers over X. So now we need to define Kleene algebra operations over here. So the first one, yes?
What is the motivation for having these three different semantics? A relational culture.
Well, I mean, my motivation here is because, I mean, if I could not show that I had more than one semantic, it would not be worth the algebraic abstraction, right? And then we can then discuss about what is the motivation for the relation for the algebraic abstraction. But I hope this will become clear very soon. Yeah. Okay. So yes. So the first, if I compose two non-deterministic functions, the idea is in this composition what I do. I first map with F, so it takes an element to a set. And then from each element of the set, I map my second function. But then the problem is that if I connect all these things, I get a set of sets. So I need to flatten that. How do I flatten such things? I apply union, right? So this is the definition, right? And I call it a Kleene composition. So because it has to do for functional programmers or people who know about categories, it has to do about the Kleene monad of the power set, or the power set monad. Some people call it the power set monad, right? And that is the composition of the arrows in this power set monad, right? So I apply my first function, then I apply my second one, and then I flatten basically the result that I get. If you're a functional programmer, you should actually complain that the order of the in this, they are usually swapped, but I keep them in that way, as people say, in diagrammatic order to make it compatible with relation compositions. Right? Okay, so then the next thing we need to look at would be the identity of that composition, and that would be the unit of my monad. It just means I map an element to its decoration with set braces, right? So, and that gives me a state transformer, obviously, because I map an element A to a set. And then, it's quite easy again to check that you have unit laws. So, for example, F composed is F, and composed is to F. And if you reason about it using these definitions, it's quite easy. And that's something you can prove automatically, for example, with the proof assistant. Zero state transformer is just a function that maps every element to the empty set. And then I need two more operations. I need the sum. And the sum is defined as some mathematicians would call it by pointwise extension, which means that if I go with F plus G from A to a set, what it actually means, I first go with F here and go with G there. I get two sets and I take the unit of the outputs. That's all it does. And it's easy to check that that's an associative commutative idempotent operation. I can define a partial order. I can define F below G simply as F plus G is equal to G, as in any semilattice. But I can also use a pointwise extension. I can say if for all elements, the set FA is contained in the set A. And again, it says that our program F, which is now a function, is less deterministic than G. And then as before, I can define my star as a union of powers, where the powers are again defined inductively, but of course this time with regard to the Kleene composition. And then we can show yes, that this would already give us a Kleene algebra. And then we need to care about our sub-identities. The sub-identities are, again, functions below the identity. So now they map elements in X either to the element itself, decorated by braces, or to the empty set. I can then define a complement, either, like algebraically or explicitly. I say that the complement of a sub-identity P maps A to A if the original function P maps it to 0, and it maps to the empty set if the original function maps it to A decorated with set braces. So you see that basically here the values are swapped, and that's why it's a complementation operation. Yeah, and then we can show that state transformers solve a Kleene algebra test, right? And then we have two models, so which is fine for justifying our assumptions. But there's another interesting thing here, and the other interesting thing is that there are other models which are also interesting if you want to do concurrency verification. So, for example, you can take, as I described before, path over directed graphs, compose these parts on their ends, right? And then do the other operations on them, and that would give you establish suitable operations of them, and that would also give you a Kleene algebra with tests, right? So even if you're in the context of finite concurrent programs where you don't have infinite operations, you could establish such a model, and there are some details in my lecture notes. But instead of doing all this routine work, there's another way of proving this equivalence. And sometimes, when it's important to compare models or semantics, you can do that by using structure-preserving maps, these semantics. And if two models are essentially the same in the sense that they have the same structure, then these structure-preserving maps allow you to show that they are isomorphic. And in fact, it's quite easy to show that rel and star are isomorphic models. So we have not gained so much after all. They are just different views, if you want. So you define these two maps, which go from rel to star. They are defined here. You can show that they are of pairs. So they basically send elements to elements in an injective and surjective way, 1 to 1 and on 2. And then you can show that these operations preserve the entire one way or the other way, and even the Kleene algebra with test structure. And then it's very easy from there, from these couple of theorems, to show basically that the state transformers from Kleene algebra with tests isn't only if rel does, because the models are isomorphic. And this isomorphism is very suitable for transporting, for example, properties from one structure into the other. So suppose we know that relational composition is associative for the class decomposition, which is maybe a bit more tricky. Then what we say is, okay, we know that S composed with R is the identity. We just plug it in front. We pull the R in. We apply our relational associativity law. We pull the R out, and we know that this is a unit, so we take it away. And then we have basically this kind of property in the other model. Right? And this is how you can prove such properties detained easily, for example, in Isabelle, instead of going through the whole work again. Okay. Now, this was basically about the mathematics and the algebraic program semantics. And now I want to turn to Hoare logic. Right? And the first thing I want to show you is how Hoare logic can be done in Kleene algebra tests in a very kind of lean, simple, and elegant way. And I can say it because it has not been my work. So let's try to derive rules for a Hoare logic in cut. How is that going to work? But with one proviso in what I call a propositional Hoare logic, because in these algebras we have always disregarded assignment laws. Yeah. So how is it done? So the first thing we need to write down is partial correctness specification, which brings us back to your question. So I don't read again what partial correctness means. I guess you all know it. But you can convince yourselves that if we cut a program X is partially correct in regards to precondition P and postcondition Q is the following inequality holds. So we can debate what is the optimal way of introducing it, but it says essentially that if I execute my program X from states that P holds, then I'm guaranteed basically to end up in states that Q holds as well. Yeah, that's what it is. And then as an abbreviation, we can introduce the notion of a Hoare triple. And a Hoare triple is just a ternary relation, which is true if and only if this kind of inequality is true. Right? So now we have Hoare triples, we can do Hoare logic. So in order to, well, I'm recorded, I need to be careful what I say. In order to not to do nonsense, we want to try to figure out whether these definitions actually make sense. So we can go into the relational model, for example, or in the state transformer model and check them, right? And then if we expand definitions, I mean, we know that basically the relations form a Hoare logic. If we expand definitions, we know that the Hoare triple holds if and only for all states A and B, if the precondition holds in state A, if our relational programs brings us from state A to state B, then the postcondition will hold in state B, right? And I think that should make us all happy. Yeah. Now, propositional Hoare logic. So these are the standard rules of Hoare logic. Shall I explain them? Everybody knows, right? I think you learn them in the second year, hopefully. In Sheffield, they are hidden in the second semester of the fourth year. I don't know why. Okay, these are the standard rules of Hoare logic. But basically, we have them now written in the language of Kleene algebra with tests. And now we have basically Kleene algebra with tests, which allows us to derive these. We can check whether they follow from the axioms. And the claim is that this is indeed the case. Yeah, and as I said, there's no rule for variables. Now, so that would be the hardest rule, the derivation of the while rule. And I was cheating a bit, to make it even. I tried to fit it into one line, fair. And, if you want to be explicit, you have to add maybe one or two lines. But that is basically the entire proof, right? So you don't need to worry about sets and relations and properties or state transformers and Kleene compositions. You just prove this little thing and it can be done by equation. An automatic theorem that can just blast it away. And same for the other rules. The other rules are easier. Yeah, it's something that you can basically just say, okay, does it hold? Yes, right? By the way, Isabelle, for instance, you could even try to generate counterexamples of such properties. So it's a quick and easy exercise in Kleene algebra with tests. And the interesting thing is, of course, that this propositional Hoare logic gives you one rule per programming construct. The structural rule, sequential composition, if then, condition and while loop, which means like if you see a program at each moment in time, it's completely clear which rule you need to apply. It's syntax directed, and it's very easy to generate verification conditions. When you see a program plus the way the control structure, you're just left with proof obligations at the level of data structures. But there are two bottlenecks, of course. One bottleneck is that in the way the sequential composition rule works, you have this intermediate pre-post condition pair R, and that can become somehow creative to find it, right? It's not completely automatic. And of course, for the while loop, as we shall see on the next slides, you need to come up with invariants. Right? So in the while loop, P is a precondition and a postcondition. And generally, you would call an invariant of a program something that satisfies this kind of condition, like a weak commutativity condition or lax commutativity condition, whatever you want to call it. And so the P is actually, because it occurs here and here, and here, it's actually a loop environment, a loop invariant, as it should be. And you can make use of this. For example, if you do verification, you can define a decorated while loop with an invariant. The semantics of it is the same as the while loop without the invariant. You just annotate it. but you can use it to trigger a different kind of while rule. And you say that the precondition must apply the invariant, so to say. The invariant is maintained when you execute the body of the loop. The invariant implies the postcondition when the test fails. And in that case, basically, you have verified your while, right? So that's what you want. And yeah, I mean, this basically summarizes what I just said. And that's what you would use in verification applications. Okay, so now the remaining bit that we need to look at is now we have this abstract semantics, we have this intermediate layer of the relational and the state transformer semantics, but we can't yet talk about programs though. So now if you really want to have a concrete semantics for programs, we need to be able to talk about the program store. And that's what I'm going in the last part, to build really concrete semantics of programs in which we can verify programs. And we will derive the inference rules for variable assignments in this concrete semantics to get a thing flavor. So again, I want to keep it very simple. For me, a program store is just a function from variables to values. Yeah. So if you don't like that, if you think that program stores should be, I don't know what, records, or, you know, like some monadic things, lenses, whatever, you can build your model and can plug it in, and it will pretty much work with the semantic setup that you see. But I want to keep it simple. And I write basically D to the V for the set of all program states, which is the set of all functions from B to D. So, of course, if you have assignment statements, you have expressions. But we don't like expressions, right? Because we are doing program semantics. Expressions are syntactic objects. So we want to get rid of them. And also when we build components later in Isabelle, we do what people call a shallow embedding. Everything is semantic. We don't want to have expressions. But in order to understand how we get rid of expressions, I first need to explain how we can define, right? I mean, so this would be a simple syntax for arithmetic expressions. And then, of course, you have an evaluation function which evaluates a function into a store and gives you natural numbers. So, by the way, quick question: how would logicians call this kind of function that is plugged in here, and how would logicians call this function? You know, are there any logicians here? You're a logician.
Oh, very bad indicators.
No, I'm talking about this function and the components here. This.
Oh.
Huh?
Negation.
Sorry?
Negation.
It's mono. So, no. I mean, this is just a placeholder for the variable that goes in. It's just stupid notation here. It's not negation. I tell you what it is. So this logicians would call the store an assignment function, right? And logicians would call the evaluation function the interpretation function. Expressions are terms in logic. This is the semantic map or interpretation function. And the store that I've set up is nothing but an assignment. It's no surprise that logicians invented programming languages back in the day. But it's kept as a secret, I think, right? But that's all there is. Well. Okay, now that's the example of evaluating expression, right? So, and I'm really tedious here at these little. It's an inductive definition, or you get a recursive function and then you recurse over the inductive definition of the expression data type, and you get a value. That's what happens. So what we are doing instead is that we are replacing the expression is by functions that have already been by semantic maps that have already evaluated up to the level of variables. Right, so where we apply our store. So, for example, instead of the expression e times 3 times v plus 9, we now use the function lambda means that basically the variable is xs. So we have the function 3 times sv plus 9 s numbers. That's all we. So, and that gives us basically expression lambda sv, evaluation of this term relative to this. because only the variables are really looked up in the store. The rest is somehow fixed. And then, you know, if we now, instead of evaluating our expression like on the previous slide, what we are doing is now we are just applying this function to a store. So if the store maps V to 11, then we need to plug it here, right, which goes on here, and then we get the same number 42. And henceforth, because I don't like these this index business, I can drop all these indices. And now the next thing we need to talk about is store updates, right? We now use these functions instead of expressions, and we update program stores. So a variable assignment, as we all know, updates a program store as follows, right? So the function that we have, our expression, is applied to the store that we have. And then the value of that E in the store S is then used to construct the updated store as prime, where S prime now maps V to ES and every other value to the value of the previous store. So if you think about a store as a kind of vector, and the vector is indexed by your variables, you update basically in the place where E sits, and you there, the new value is E, ES, and everywhere else the store stays the same. In order to define that, you can define a store update function, which is some sort of higher order function which takes a variable and a value and a store and another store. And what does it do? If you give this function basically a variable, a value, and a store prior to execution, and then here the other store, a map from variables to values, so you can feed it another variable, right? And what you get is if the variable v prime is equal to v, you return the value, and otherwise, if the two variables are distinct, then you just do nothing. So the function will be s of, the value will be s of, yeah, and it just updates the store in the way we previously described. And because in the setting of program assignments, so this component is usually not a value, but it's one of our semantic expression functions that we need to evaluate. I introduced this abbreviation set v to e in the store s, which is basically like the update v at the value es in s. It's difficult for me to explain that, but I think the mathematics, when you look at it, it's probably easier. So, for example, I mean, how would that work? So let's take our expression function again, so the e, and assume that in our store, the variable v is mapped to as before. Right? So now what we are doing is that we compute basically the new state s prime, which is set v to e in s, and then we just do the same exercise as we have done before. So, and if we, now we need to take this function, evaluate it, that gives us the value 42, as we have seen. So now the result that we get is our update function. Update the store in, let's say, coordinate v by 42, right? And that's what we get. And yeah, that would be, now if you check the result, right? So if you look at what the new store looks like in the v coordinate, it will be 42, and in all other components, of course, it will not have changed. So now the interesting thing is that you can algebraize the effect of these kind of store updates too. And here are 5 algebraic laws. So the first one says that if you basically update your function, update your store by assigning d to v, and then you look at the value in d, of course you get in v, so of course you get d out. I think it's really time to stop. I'm losing concentration. And if you do it at another value, you just get s v prime. That was cases in the definition of the function. Then if you do one basically of these updates followed by another one, and you don't see the effect of the second update and not of the first. If you execute 2 updates on different variables, so basically different places in my vector, that commutes, so I can do both orders. And then the last one says, if I compute the value in my current store and then assign it back to the value S, nothing changes. I mean, my store doesn't. And they help us really to understand how delta and set also, you can have similar laws for set, how they act on the program store. Do you know how these laws are sometimes called? Functional programmers, category theorists, Lenz laws. Have you heard about them? These are basically Lenz laws, but they are very old. I mean, I could trace them back to McCarthy, the inventor of Lisp. So already in the 1950s or 60s, people were saying these are laws that we call for variable signs. Okay, and this is first. Right. Thank you. So I assume summer school means that brains are on holiday. Mine is on holiday anyway. Okay, good. So I finished my slides, and then we will start with Isabelle. So what we saw now was this setup for this kind of update functions. Oh, now that's very high up. And now we need to define, we use that to define the semantics of assignment. But this is really easy now, because what we do in the state transformer semantics, so V gets E in state S, just means set V E to S. That's it, right? So if your semantic is defined in a nice way, then suddenly, you know, everything becomes very easy. The only thing that really, I'm recorded, is not optimal, is that I have to decorate this with set braces, right? I mean, of course, the computation of the new state for an assignment statement is completely deterministic, right? And the only reason why we have actually introduced non-determinism was to write the while loop as some sort of sub in the semantics. That's why we needed it, right? So straight line programs where we have no while loops, you can basically just calculate the assignments one after the other. You know, if you have an if then else, you calculate them for branches and so on. So why to make the fuss? Well, we need to make the fuss because we also deal with while loops. Yeah, that's it. In the relational semantics, the semantics of the assignment statement can be obtained by applying this functor R, and then we can just use the thing that we have already computed for the state transformers to get us the relational expression. And that's essentially just the graph of the other thing. But it's not quite the graph, of course, because we need to get rid of the set braces along the way. So that's now the assignment. And because they are so similar, you know, one is just the graph of the other, essentially I just write assignment statements like that without actually annotating whether they live in the relational semantics or in the state transformer semantics. And now we can basically derive the rules of for logic. So the thing is that in our concrete semantics of the program store, we could call it something like, you know, cut of the relational program store or the state transformers over the program store, we can now derive the two classical laws. And I think I do not really need to discuss them. The first one is maybe the more intuitive one. And the second one is the law that you usually see in Hoare logic. And there's also another, and they go backwards. They are rules for backwards reasoning. So from postconditions to preconditions. There's another assignment rule which goes forward. And that's why Mike Gordon at some stage wrote a paper called Forward with Hoare, because he was using this other assignment rule in Hoare logic, and that's Floyd assignments rule. I do not want to discuss it here, but you can find it, a derivation of it in the lecture notes.
There's a question.
Yes?
It's quite a minor one, but why do you use, I thought you were using ever so slightly different notation for the triples.
Oh yes, because I'm too lazy to write all these set braces. It's just notation, yeah. And also, you know, if you work with a proof assistant, it's more convenient to write it like that. That's the only reason. But I mean, ultimately, I don't like Hoare logic. But I can tell you offline, I like predicate transformer semantics much more. They are much more natural from a mathematical point of view, I believe. And there, this question does not even arise. Okay, so if you want to derive the first law, again, you see it's just a couple of lines of reasoning. So in the first line, you unfold the definition of the Hoare triple that we have already seen. And then the crucial thing, and my arm is not long enough now, so as in mathematics departments, they usually have sticks, right? But I think... But yeah, no, it's all right. But I think here today in universities, sticks are deemed too dangerous, to handle them in classrooms. Anyway, so there's this crucial thing is that S prime is an element of this kind of set. But because this is a singleton set, we can just write in the next line, S prime is equal to the set, to set of something. Ah, yeah. So there's this new technology, a laser pointer. Great. So that's why trees can grow and people don't prune them. So from here to there I was talking. And once you have this expression, you can just substitute this, the right-hand side for the left-hand side in Q, and that gives you this expression, right? And this is how you derive the Hoare triple, the Hoare triple for the assignment law, this one. And then there's the other law, which is basically this one, where you don't have this kind of implication, but you just put basically this kind of update of the store into the precondition of the Hoare triple. And when people talk about Hoare logic, they just make a big mystery about it, and they give lots of examples explaining why you put the effect of the update on the precondition and not on the postcondition. But if you do that in the using this rule derived, it's very natural, because all you do, I go back, is you say, okay, suppose that the P and the Q are the same, right? So you have PS is equal to this one, and then you can basically, the antecedent of the previous definition reduces to true, and you substitute basically the Q of set VES for PS in the Hoare triple, and then you get what we have seen. So there's no mystery here if you do this derivation at the semantic level. And now these definitions have been in the state transformer model because it looks much smoother somehow at the level of the stores, but the derivations in the relational model would be almost identical, right? So as I said, the assignment laws, they work backwards, and the assignments affect basically preconditions. So when you do Hoare logic, you start from the postconditions, you work your way through, to the preconditions. And now we have a complete Hoare logic, and we can start verifying programs, right? So what the benefit of algebra is, there was this question, why do we use algebra? In this context, it's precisely that we don't need to worry to deriving all the rules of Hoare logic except for the assignment rules in the concrete semantics of programs. We do it once and for all in Kleene algebra, and then in all the models, whether it be state transformers or relations or traces or whatever your favorite model might look at, it's there already, right? Once you prove that your model forms a cut, you don't have to derive all these rules. The only thing that you need to look at are the assignment laws, and that's it. And that's one of the benefits of algebra in this setting. Good. So here's an example of how the assignment affects assertions, right? So suppose we have this predicate and a store, and now we just want to see what happens if we update the predicate. So the predicate depends on the variable v, and now we update the value of the variable v in the store s by 7. And we take an arbitrary store because it doesn't matter. And what you see, the effect of this application of this function is just that the v is replaced by 7. Big magic, right? How do we get there? Well, we just apply one of these lens laws, right? So because we know that we have a v here and a v, then we get the 7 out. That's how it works. And then here is another example where we have a more complicated example. So what we do is now we update the store by 8, right? And in this case, basically, we replace v by the value of v in the store plus 8. And then this v here, we apply v to it. And that means now we get this value out here, which is the effect of that, right? So it's always, these kind of updates in predicates and so on, they replace variables by newly computed values in the store. Yeah. And by the way, I mean, those of you who know Hoare logic, so they say, no, you don't replace, you substitute, right? So in Hoare logic, often you see these substitutions, right? But again, we have already discussed that in logic, a store is nothing but an assignment. And the semantic functions that we have, they come from interpretations. And in first order logic, for example, you have several ways of defining the semantics of existential and universal quantification. You can say once you substitute all possible values, if you have a for all quantifier, or you say in your model you replace all elements, the elements that you have in a model by all other possible model values that you have, right? And this shows up here. We are at the semantic level, so we are working with replacements. Some people like to do Hoare logic at the level of semantics, and then they would work with substitutions. But if you really think about it, right, if you write basically V gets E, what does it mean, right? It's meaningless. A variable cannot be equal to an expression. It's nonsense, right? So behind the scenes, you always think semantically, and you always think when you see an assignment, the value of the variable in the store is equal to something. And at this semantic level, we make all these things just very, very precise. Okay, so now if you look at verification examples, so this is what you typically see in textbooks, and you don't see the H, you see these brackets, but as I said, you know, the variable is equal to, the variable Q is equal to 0, it's nonsense, right? You need to add the semantic information in your mind in order to understand what's actually going on. And if you do that, what you do is you just decorate this program with a couple of store symbols and with these kind of lambdas, right? So that's what is going, but when you go from these kind of, let's say, sketches of Hoare logic at the syntactic level to this level here, yeah? And yeah, now let's look at a very simple Hoare triple, right? So we execute a program, Q gets 0 in any store. So what do we expect the post condition to be? Well, we expect that Q has now the value 0 in the store. We are precise about that. And the precondition is true, and true is decorated by a lambda, because obviously we have semantic functions that depend on the store. That's basically why it's written like that. And now if we verify it, right, we basically use the Hoare assignment law, H assign, if and only if. That gives us this. True goes away. Now we have a quantifier for over all states. And what is now going on is basically we substitute 0, or we update, we replace, I should say, because we are doing semantics. So we basically replace Q by 0 in this computation, right? And then you see at the end, 0 is equal to 0, which is true, which means that this Hoare triple here is valid. Yeah? Then the way people write this down is rather as sometimes as these proof outlines. If you do proofs by paper, I don't know whether you know them. You start from the post condition, and now you know that that Q gets the value 0 in the store S. That means, you know, if you move up into your precondition because of the assignment laws of Hoare logic, now you need to replace this by 0, as we have seen on the previous slides. So you have 0 equals 0, which is the same as true, right? And what people usually do in these kind of proof outlines, they even get rid of the store references and they just write it down like this. And this is maybe how you have been taught it. And if you are, you know, like in your 30s or 40s, and you have been taught Hoare logic, for example, by Mike Gordon at Cambridge, that's how you would verify programs. Yeah. And by the way, I mean, all the stuff that I'm doing has been really, really strongly inspired by Mike Gordon's work. The only thing that he has not used in his work is Kleene algebra, because he's basically set up his way of doing Hoare logic in Hoare in the 1980s when Kleene algebra was not yet around. So here's another example. We want to check validity of this one, of this assertion, right? So if we start with, if the variable Q has the value n in the store and we increment it, then it should have the value n plus 1, right? And then again, we use our law of Hoare logic here. And then what's going on is that Q will be replaced by the value of Q in the store S plus 1, right? So it's again this kind of thing. But because our assumption here is that Q, S of Q is equal to n, then this here reduces to n, and we get n plus n, and the whole Hoare triple is again. So these are really precise semantic calculations of these Hoare triples that you can do in a proof assistant, and the rest, if you have more complicated programs, it's just program structure. Again, you know, you can translate that into these kind of proof sketches from the post condition. You see now Q will be replaced by SQ plus 1 here, so you get that. And then you can show that the precondition implies this Hoare triple here, which is what you need in this context. What people traditionally write is more like a proof sketch in this way. Yeah, or proof outline, sorry. Yeah, proof outlines can, of course, be composed, because the store never changes if you work your way up from the post conditions. If you just have assignments, you're always basically keeping the same store, you just update it. So you can accumulate these update functions, and this information can be used to compose these things, right? So now if you write such a proof sketch for the integer division algorithm we started with, it would be something like this, right? So you have your precondition, you have your postcondition, then you have your invariant for the while loop. Then when you execute the while loop, the invariant must be true and the test of the program. If you exit your while loop after one iteration, you must maintain the invariant. Now, if you see basically the assignments here and here, the values are substituted. So that means for R, you substitute R minus 1. For Q, you substitute Q plus 1. Before the loop, you have your invariant. And then again, here you need to substitute X for R, which gives you this. And you need to substitute 0 for Q, which gives you that. And then you multiply X equals 0 times Y plus X, which gives you true. So why do I need this precondition? Yes?
Is it because when you're automatically verifying that you do need to start from, that you need the precondition to be...
No, you can start from true. You just need it for termination. That's the deal, right? But here we are doing only partial correctness, so it's not an issue, okay? That's it, and now we've gone full circle. Yeah? So now we can, in this kind of semantic framework, verify our program. Yeah, and I think, yeah, I mean, okay, so we went through 3 semantic layers, right? So we have basically first Kleene algebra with tests, then our semi-concrete semantics, which are given by relations or state transformers, and then we have added the program store to that, a very simple one, and this approach is completely compositional. So you can change the algebra if you need to. If you want to do, for example, total correctness, you need to drop some zero laws. You can change the semantics if you don't like state transformers relations. In the context of sequential programs, partial correctness, I think you can plug in others. If you don't like the simple program stores, use your own, right? So you can do that. Approach is also extensible. So there are many variants of Kleene algebras. In particular, you can use variants of Kleene algebras to use predicate transformers instead of Hoare logic, if you like predicate transformers more than Hoare logic. And in the past, there have been many, many applications of Kleene algebra in various different fields. I just want to mention one I've been involved in. It's basically a hybrid program verification in the style of differential dynamic logic invented by a guy called André Platzer. I don't know whether you know about it. It's basically the standard for hybrid program verification. And he built a very, very complicated proof system for that, implemented it from scratch in a theorem prover, that Chimera X, that took ages to develop. And so what we did is we just took our framework, similar to what I showed you, and we just plugged out the standard program store. We plugged in a store in which you can reason about dynamic systems, you know, differential equations and all this kind of stuff. And then we could basically verify enough programs to do most of the proofs in their kind of theorem prover verification challenges, right? So it has been really a great simplification of this approach. Essentially, this differential dynamic logic more or less reduces just to a standard Hoare logic plus a different program store, or a standard predicate transformer semantics if you want to use it. Then now towards proof assistance, right? So if you know the trick of the trades, then you can use basically, and if they are mathematical components, you can then specify verification components based on the stuff that I showed you very, very easily. So the choice that you have these days is mainly between Kleene or Isabelle. So Coq is great for formalizing mathematics, much better than Isabelle. But more or less, if you use Coq, you need to do your own proofs, right? So there's not much automation. Or if you want to have automation in many situations, you need to write it yourself. Yeah. So Isabelle is sometimes limited if you want to verify, to do really substantial mathematics. But it offers great proof automation and counterexample generators. And for these kind of simple verification things, it's really, really suitable. Lean, there's a lot of propaganda about Lean, in particular amongst mathematicians at the moment. And so the idea here is to combine the lessons learned from Coq and Isabelle. And I think there is definitely scope for a new kid on the block or something like that. But if you use it in practice, it feels much more unstable and immature, right? So many things that I could do easily in Isabelle or in Coq, I don't know how to do them in Lean. The documentation is not so good, right? But these are essentially the choices that you have. And so I want to show you how to do everything in Isabelle. And because my approach is purely semantics, I can use what people call a shallow embedding, right? Which means that in order to talk about my semantic functions and so on, I do not need to define new things. So I can basically use all the functions, relations, and blah that already exist in Isabelle, right? And that makes it slick or easy. And whether you do it, and if you want to have program syntax, well, write your syntax as a grammar and then write your interpretation functions. But that's box standard. I mean, there's not much you can really learn from it. Whether you do all this in Coq, Isabelle, or Lean doesn't really matter. I mean, the approach will ultimately be very similar. So the mathematical components that describe everything I've done so far can be found in the archive of formal proofs, which is where people in the Isabelle community upload their code. And here in the little framework I give you, I use a condensed component, mathematical component. And if you print it out as a PDF, it's around 30 pages with all complete and very detailed proofs. And then the proper verification components that are built on top of it would only be 10 pages. So if you know what you're doing, you can basically use these components and build your verification components over a weekend or so. So for example, when I had my Hoare logic and I wanted to turn that into a refinement component, program refine component in the style of Carol Morgan, I could do it in an afternoon. Exactly. And then again, you know what I said in the beginning, if you want to play around, there's a template on Git with proof holes. You can learn about how to use Isabelle using that, and you can ultimately build your own verification component in which you can then verify integer division. Isn't that great? Okay. Anyway, that's it. And now I need to switch gears and sit down and see how it goes. So I need 1 minute maybe or two. Yes. Okay. This is Isabelle. Right, so this is the standard user interface. Code JEdit. And this is too small, right? I need to make the font larger, right? Good? Yes? I need a balance between, you know, what you can read and what I can show. Okay, so what I do here is I basically define a component that is called KA for Kleene algebra, and it imports Isabelle's main libraries, right? Which is, you can imagine, you know what a main library is. And now I start with monoids. And I want to use notation. I mean, Isabelle traditionally uses the star for multiplication. I want to use this little dot here, and I can declare that. And then I use what is called a type class for declaring my algebra. And the type class is, you know, for those of you who know functional programming, It is basically like a collection of types that satisfy common properties. For us, a type class is simply a context in which we can declare an algebraic structure and then reason about it. Yeah, that's what's going on here. So for example, this is what I have typed in order to define a multiplicative monoid, right? I use an operation times. If I hover over it and click, whoops, and I do it in the proper way, it sends me to Isabelle's main libraries where the class times is defined. And that's a class that just fixes notation. It introduces an operation of a times a to a, but the slogan in all these kind of proof assistants is that you should carry your functions. So it is basically a function that takes 2 arguments, and that's it. And you see there are also classes for plus and minus and blah, blah, blah. Okay, let's go back to my thing. So now we have times 1. The class 1, you can guess what it is. It's a class that gives you just the constant 1 with notation. And then I can write down my axioms, right? Assume mult assoc blah, 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 gives me the associativity laws. Then I have the unit laws. And then I could type something like begin, end. Now I have a context in which I can prove stuff about monoids. So let's prove a lemma. So now we can prove, I don't know, x times bracket 1 times y is the same as x times y. It's a little bit silly, right? And yeah, I mean, this is now basically a lemma. And now let's try to prove it, right? And what you see is Isabelle is using built-in methods that are called solve direct, quick check, try zero, which are lots of tools, sledgehammer, and nitpick to tackle this goal. Interestingly, quick check and nitpick are counterexample generators, which did not find anything. And then sledgehammer is a tool that calls external first-order theorem provers and SMT solvers, which are glorified SAT solvers, tackling these goals. And then these tools return here, for example, CVC4, a SAT solver, then Z3, I guess here, another SAT solver, zipper position, Spaß, vampire, first-order theorem provers, and they found a proof, right? And if I click on this proof, it comes into the context here, and now I have proved my first lemma, yeah? Okay? And this is when you're a beginner with Isabelle, that's the way you proceed, right? So you write down your theorem, then if you are Catholic, you start try, you go to church, you lit a candle, pray to the Almighty God, and then maybe you get a proof, right? So that's how it works. And now, if you make mistakes, for example, in a specification or something like that, so let's assume you have this. All right, and now let's try to prove it. And now you see we get, yes?
How do you get the nice LaTeX symbols? Mine comes out as
LaTeX, and then you tip tab. Tab. You type the beginning and you tab, and then it should come. I can show you in the break.
So escape first. Escape and then tab.
Okay, yeah, thank you. If people have Isabelle questions, you can go to the pub in the evening, right? But if you have many questions, it will become expensive for you. But anyway, so what we see here is Isabelle said there's a counterexample, right? So it says nitpick found a counterexample for cardinality 3, which means that we have a model with 3 elements which falsifies that claim. So falsifies means that we have basically a model in which the monoid axioms hold, but the commutativity law fails, right? And if you get a little bit trained, you can basically see that this is actually a multiplication table. So what does it say? It says basically here, x is basically a times a1 times a1 is a1, a1 times a2 is a2, a1 times a3 is a3, a2 times a1 is a2, and so on and so forth. You can imagine, right? And you can draw a nice table, with your elements. So the elements here would be A1, A2, A3. So you get basically something like a 3 times 3 matrix, and then you can basically and put it into your papers if you need counterexamples, right? Which is something that you would not get in Coq or Lean. Also, the automation, of course, does not work because Coq and Lean are prima facie constructive, and there are no nice automatic theorem provers for that. Okay, so that was really trivial, and Isabelle figured it out anyway. It said already, you know, without me trying to do anything, quick check another counterexample, found a counterexample here. Okay, now we can define additive monoids, and that uses the extension. No, it does not use the extension mechanism, not yet. So now we basically do the same thing, but with a plus and a 0 instead of the times and the 1. And then we extend that to additive monoids, because plus is usually a commutative operation, right? And now the Isabelle's class extension mechanism comes into play. We can basically say a commutative or abelian additive monoid is an additive monoid plus the commutativity law, yeah? As simple as that. And then we can go further and we can say that a semilattice with respect to sub, which is plus, is a commutative monoid plus odd. So here, look, I mean, here I have an additive, abelian additive monoid. Here I'm using another class, which is called monoid add. So this is now a built-in class from Isabelle's main libraries, right? I showed you these two monoid classes only, you know, for the sake of it. And now I'm moving to using Isabelle's classes. Now, I also need something like odd, a class called odd, and that just gives me an order symbol, because remember, in the semilattice, I had an order, and I add that to the class. So now a subsemilattice is a commutative monoid, which satisfies the Stalinist choice law, x plus x is equal to x. And then the order is defined by saying that x is below y if and only if x plus y equals y, as before. And then what is a little bit nasty in Isabelle also asks you to define a strict order. And the proof obligations for that are always the same, right? But Isabelle has been designed by most of the mathematical components have been built by computer scientists and not by mathematicians. So now we don't know yet that Isabelle that this symbol is actually an order symbol, but I can ask Isabelle to prove that. I say, okay, subclass order. Now I need to look at my sheet in order to see how I do it precisely, because I want to be a little bit consistent. So now what I can ask Isabelle is to show me the proof applications for that. And I see them in the window down here. And I need to write, for obscure reason, unfold locals. Oops. And I need to say apply. And I need to put an underscore between these. Voila. So you see, you know, if I type nonsense, Isabelle will complain. It's like in a type programming language. Yes?
A bit of an Isabelle question, but is there a reason that you're using type classes instead of locales?
I use type classes instead of locales because I find them more elegant and much simpler. Local, I mean, there's a limitation. It's some kind of meta question. So Isabelle has the limitation that in a type class I can only have one type parameter. So in more general settings, I would be forced to use locales. But Isabelle has a very weak type theory compared to Coq or Lean. And it means when I use locales, I'm basically leaving this type theory universe. And I don't like that. I like types more than sets. Yeah, and then I always try to stick with type classes as long as I can. Yeah. You don't have dependent types. I mean, what you can code in Isabelle's type theory is actually quite limited. Okay, but in any case, I type unfold locales, and now Isabelle tells me, right, if you want to prove that you actually have a partial order, you need to prove these 4 properties down here. Right? Isabelle basically dictates the proof obligation, and what can I do? Well, I can say try. Yeah, look. And then the provers come back and they give me various options, blah, blah, blah. And then I try all of them. And then for such simple proofs, Isabelle just goes through. And after that, I know that semilattices have a relation which is a partial order. And at that moment, Isabelle has its own theory of partial orders, which can be found here if I hover and click and look. I mean, there are lots of properties, and all these properties are now in scope. I can use them for my proofs. I don't want to continue that, right? It's boring. You just see me typing try, Isabelle giving me an answer, and then me finishing the proof. Okay, now, if you remember on one of my slides, I showed that now in the semilattice, 0 is the least element with regard to this order. Yeah. How do I prove it? I try, right? I type try and I will get an answer. Yeah? Oops, no, wrong place. Here. Sorry, by the way, means that Isabelle allows me to proceed to the next lemma, but the lemma that I write is not, and the lemma that I have is accepted, right? So there are two things, sorry and oops. Oops means, okay, ignore the lemma. You can write it, proceed, but the lemma is ignored. Sorry means that it's a bit dangerous, right? But sorry means that the result is accepted and I can use it in further proofs. So again, I try it, I prove it, right? It's getting boring now. But on the other hand, very effective. So imagine that you're prototyping with axioms and assumptions. So this style of reasoning is really effective. So here's an example that I want to show you, which shows that you can also write nice proofs in Isabelle. So for example, sometimes, you know, these theorem provers, they can't prove everything. And sometimes you get stuck. And this is where the role of these provers as proof assistants come into play. And so what you are doing now is you have this proof scripting language, which is called ISAR, I-S-A-R, which is a river flowing through Munich. And for some reasons, the Isabelle people like to use place names around Munich for their tools, right? Eisbach, I mean, who can say Eisbach if you're not from Germany? I don't know, but these are the names, right? But this is now a proof called in ISAR, written in ISAR, and it's actually the proof that you would write by hand if you look at it, right? So I want to show this property under this hypothesis. So I write, assume the hypothesis. I can even give it a label so that Isabelle can refer to it explicitly. And then I say, from the assumption, hence, x plus y is equal to y, which is simply the definition of the order relation in my lattice, right? I try, I get a proof, and it says, well, use the definition of the order relation. And now what I'm doing is that I'm essentially adding z's at both sides. So I add a z here, and I add another z on these sides, and I can add two z's here because addition is idempotent, right? And then I can say from this I can derive that y is equal to to z, and that uses the assumption x plus y is equal to y. So that means basically that here the x plus y becomes just the y. Sorry, no, I'm working on this side. It's like an equational proof. So the x plus y just becomes a y, and then I'm here. And then I can say, okay, finally have this is equal to that. So I can really write these equational proofs that way. And then I just add a dot. I mean, I could also call try, but this proof goal is, proof goal is trivial. So I just type dot and Isabelle finds it. And then I say thus, which means that at the end, under these assumptions, prove my goal. And I could even write more briefly from this, prove the thesis. Right? And then I do another try and my proof is done. Yeah? So this is essentially how you're doing these little proofs with Isabelle. So you can add labels if you wish in order to tell, use an hypothesis named A, which I do at this place. If I don't have this A, Isabelle will still find the proof. But it will now add this x plus y is equal to y, which looks not as nice as the A, right? So that's the reason why I added the A. Okay. Yeah, and then you see, here are now many little lemmas in my proof templates that I gave to you that you can actually use with Isabelle, either to do these proofs automatically or also to try to do first proofs by hand and then use Isabelle as a proof assistant to type in these proofs line by line, following this little template and looking at Isabelle's documentation And then you can work your way through these documents, right? So the next class would be a semi-ring, which is an additive monoid, which is commutative, and a multiplicative monoid. Then we add two distributivity laws. And then we can go on to a Kleene algebra, where we define as a class that only has the Kleene star. Then we add the axioms that you have seen, and then we can basically try to prove laws about the Kleene star. Yeah, and you see again, Isabelle finds these little laws automatic. And mainly, I mean, okay, so now when the lemmas, when the things that we have in the lemmas become more complicated, so like, for example, I don't know, I have properties, look where I give, I don't know what's going wrong here now. What did I do?
Sorry.
Which one did I not sorry? Oh my God. Ah, yes, exactly. So you see, I mean, that basically shows, is a proof that Isabelle indeed brought all these lemmas from about orders into context, right? So yeah, now you can even do proofs by induction with Isabelle, right? That's a nice thing. So for example, we want to show that x to the I is below x star. This is also an operation of power which comes from Isabelle, lives in yes?
Rather than asking each lemma in turn, I don't suppose it's possible in any way to...
Sorry?
I don't suppose it's possible in any way to get it to list the interesting things that can be said from a certain starting point.
By machine learning or what?
Don't know, just that's
Well, I mean, so usually, I mean, I'm basically, I mean, it's, you know, like in communism, the user owns the means of production, right? I tell Isabelle what to do. Yeah, it's and I think everything else. I mean, you had a project a long time ago on teaching this kind of learning stuff to.
And they have a revival now.
They have a revival, but do you still know what's going on?
Yeah, I mean, it's if you have a pattern in a proof, then it's easy enough because all these large language models, they can pick up patterns and they can reproduce for your proof. So basically, if as a human you can prove something by analogy with some other language, that's a solved problem basically, it's just a matter of tuning. But if it's a concept invention, if I did know that the star was needed in Kleene algebra, these tools are not very good at inventing that the star is needed.
Yeah. Maybe it will take a couple of years, right? But I think, so, for example, the mindset of mathematicians is pretty much, we want to control what's going on, right? I mean, these kind of lean people, these ambitious young mathematicians, they are doing very complex mathematics using lean, but they are really proving these things line by line, right? And building hierarchies of structures in the Bourbachian way or something, and then just controlling at every step of the proof what's going on. Yeah, that's the way it works. And even, you know, when I work, right, of course I can have a complicated proof. I throw on the automated theorem provers, and they give me a proof, and they list the lemmas used, right? But I do not understand what's going on. And then maybe I want to use a variant of the same, let's say, mathematical structure, where some axioms are missing or have changed, and I want to see whether I still get the same results. Then if I have a machine-generated proof, basically just this one line, apply, or do this and this and this and this, I do not know what goes wrong. If I have expanded proofs line by line, I see in which line the prover gets stuck, and I see, oh yeah, I can't do this because, I don't know, a distributivity law is missing, right? And then that gives me information to somehow fix the proof, work around, or something like that. I mean, it's the same discussion that we have a big NLP group in my department, and so the young guys are all doing, you know, statistics with Python, and the old guys, they say, you know, we don't understand anymore what's going on because they don't control basically these Chomsky grammars and whatever they were using in the past. I think it's this trade-off. But of course, verification is not a beauty contest, right? I mean, it's not like mathematicians who want to have nice proofs. I mean, you have a problem, you want to prove by all means, but it has to be checked. And then, of course, such methods, I think, will probably become very, very valuable in the future. I mean, another thing is, for example, learning loop invariance. And then, you know, like 10, 15 years ago, there was a lot of talk about a tool called DICON, but it never really caught up, for example, in these kind of theorem provers. Do you know what the state of the art is in this?
Yeah, there is a program synthesis group in Texas. If you look for Cobol tutorial from last year on
Yes.
symbolic reasoning, they do program synthesis, and this
Yeah,
is
yeah.
exactly the motivation.
Yeah. I mean, very interesting questions, right? But I think it's still somehow in the beginning in many ways, right?
Yeah, there is always debate when we discuss this. Some people believe that this will never be able to do mathematics. Machine learning will never be able to do real mathematics. And
But
some
it's
people
stupid.
believe it can be.
But it's stupid that people make these strong kind of assumptions. It's like you know, like a religious belief that you hold, right? So you need to have evidence for your claims, and I think it's impossible to give evidence what will be possible or will not be possible in 25 years, right? So people should just try, and then they will see what works and what fails, right? That's how science works, no? Okay, back to Isabelle. Yeah, okay, so you can also do proof by inductions. So if I just tell Isabelle, okay, do a proof, use induction with regards to I, Isabelle gives me a thing I can click on, and that gives me a proof template, right? The power is defined recursively, right? So there's a recursive data type. For every recursive data type, there's an induction principle. For simple data types, Isabelle knows what the induction principles will be. And now even for quite complicated stuff, thanks to Andrei Popescu, who will be teaching tomorrow, I guess, Isabelle can figure out what induction principles would be. And so here Isabelle tells you, you know, I mean, tell me in the case of 0 what's going on, and in the induction step, tell me what's going on in the 1 plus x plus 1 step. So if I would try here without doing induction, Isabelle could not figure it out, because the methods that we have been using are beyond first order logic. Induction is a second order, a higher order principle, because I quantify over predicates, right? But as soon as I know what my base case and my induction step is, then these two proofs are usually first order again and calculational, and then I can go back to my automated theorem provers, right? So that's how it would work. Okay, and then so on. I can prove a lot of stuff, and yeah, and then the next thing I wanted to show you is the following, right? So now we have our algebras, and we want to link the algebras with semantics, right? So I want to be able to say, for example, the natural numbers form a multiplicative monoid, yeah? So how do I do that? In Isabelle, there are two mechanisms for that. One is called by instantiation, which again lives in the type class world. Then the other one is by interpretation. I will show you one example or several examples. And that, again, lives in the world of sets. And again, you know, my standpoint is I prefer to do instantiations for various reasons, but there are limitations. Sometimes you need to use interpretation statements. So what do you need to do? In this case, I want to show that natural numbers form a multiplicative monoid. That's the statement I want to do, and then I need to begin doing something, nothing changes. And now I need to do an instance proof. And Isabelle here tells me, okay, I think I know what you want to do. Because Isabelle itself now needs to figure out that it actually needs to identify the multiplication on the natural numbers with the multiplication on the monoid, and the number 1 with the 1 in the monoid. But for such a simple case, Isabelle figures it out. I say instance proof, and then I can type something like apply intro classes. So this is just stuff you need to learn, right? And then Isabelle generates the proof obligations, right? They say if you want to show that the natural numbers form a monoid, you need to prove the associativity law and the identity laws, right? And this is basically what I've done. I copied in the laws that I need to show. And so all these laws are universally quantified. So I do what a logician would do. I say, fix my x, y, and z, and then prove these laws for these fixed but fresh, so to say, variables. And then again, I can do it, trying to do it easily. And then I write QED. And now, in my theory for natural numbers, I have all the abstract laws of monoids and all the lemmas I can prove in a monoid class, if any, to work, right? So here's a thing that is slightly more complicated. Well, I can also prove that, for example, natural numbers would form an additive monoid. Again, Isabelle can figure out that I would have to use addition. So this I want to skip. I mean, this is too complicated for the time being. But what I want to show here is that sets, that was one of my examples, sets form subsemilattices. Yeah? So if I take sets with regards to union and to intersection, they form semilattices. So I type in this statement. And now look, Isabelle is now not silent. Isabelle says, look, Georg, you need to tell me what 0 of the semilattice is in the context of sets and what the plus operation is in the context of sets. So I need to match these operations. And I do that by giving these definitions. I say, okay, the plus is basically the union, and the 0 of sets is the empty set, right? And after that, I can start my instance proof. I type again, apply unfold intro classes, unfold locals would also work. Then Isabelle generates the proof obligations, right? And then I need to prove all these kind of things, yeah? And again, I try and try and try and try 6 times. And then in these simple cases, it will work. Now, here's another example when I want to show that intersection is also a subsemilattice. So I now try to do the same thing, but tell Isabelle to use now intersection and the whole set X, which is called unif in Isabelle in this case, as the 0 and the multiplication or the addition, whatever you want to call it. And then I can't do that. Isabelle will not accept it. There's a limitation, but it also exists, for example, in Kleene, that for each type class, you can have only one instance per type. So here I basically need to go to interpretation statements, which come from the locals. And now the syntax is slightly different. So here I say, basically, I want to show that I get a subsemilattice. And then Isabelle asks me for what? So what do you want to have a subsemilattice for? And I say, well, for sets. So I need to tell Isabelle what the addition will be, what the 0 will be, and what the order relations will be. And this is what I have declared here, right? So now Isabelle can match again the operations. And now if I write apply, and this time unfold locals, Isabelle generates my proof obligations, and then I can proceed as before. Yeah? Yes?
You said for each type class you can have at most one instance.
Yes?
Why is that?
Maybe ask Andre on Wednesday. You know, he's one of these core Isabelle people. I'm just a stupid user. Yeah. But I mean, it seems to be a systematic thing. I mean, I'm not sure about Coq, but I know in Kleene you have precisely the same problem. Yeah. Anyway, and then proceeding this way, we can then show, for example, that relations form Kleene algebras, right? And in order to do that, I mean, it's really frustratingly simple, right? So I tell Isabelle I need to do an interpretation statement here. I can't do an instantiation statement for reasons I do not want to explain. So I tell Isabelle, you know, how to match the operations, and it's clear what I do. I type unfold locals. I get 13 subgoals, and then I can just blast them away in one go by using Isabelle's auto tactic. Why? Because the proofs, you know, I mean, you have seen how I did associativity of relational composition. It's not that easy. It uses set theory. Why is it so easy? Well, there's a very simple answer. So Isabelle is 25 or maybe 30 years old, right? It's not a young girl or anything. So, I mean, they are all already very well developed libraries for for relations in Isabelle. So that means basically Isabelle picks up lots of proofs and simplification rules, and then, you know, it can do that. If you would do the same thing in Kleene, where relations are rather underdeveloped, you might have to do some work, right? Okay. And now I do some additional definitions. So for example, I mean, I need to tell Isabelle what the star operation in relations is, and I prove a couple of lemmas. And then you see, you know, then you come to the place where you can then show that Isabelle, with Isabelle, that binary relations form Kleene algebras. Yeah. And then after having done that, everything I have proved before for these, what I have proved before for binary relations, for Kleene algebras, is now in the scope of binary relations. So in particular, all these little laws for the Kleene star that you showed on my slides, you can have then available, and you don't need to prove it yourself. You know, that's basically how you glue these libraries together in Isabelle. And then you can do the same thing for the state transformer model, right? In Isabelle, you just say that a state transformer, alpha, that's the type alpha star, is nothing but a function from A to the power set of A. That's basically the notation that you use. And then we can define all these kind of constants that we had. So basically the unit of the monad, which wraps every element into set braces, the empty state transformer, which maps every element to the empty set, the Kleisli composition here, the addition, the orderings, and so on. And then here, the work starts, because the state transformer model is not well developed in Isabelle, right? And you can see now, I mean, these are basically like a minimal set of lemmas I needed to prove my interpretation statements later. But you see, it goes on a little bit, right? And this is, for example, the proof of associativity of the Kleisli composition. Right here, I can say, okay, how do I do the proof? Well, fix two elements x and y. Suppose that y is in this composition applied to the element x. And then I show in the end that the y is also in the element that comes from the other side, right? So x is in one element if and only if it is on the other side. And from that, I can conclude the thesis, because as I said my previous lecture, two sets are equal if and only if they have the same elements. And that's what I'm using here. And so on and so forth. And then, yes, I could do this proof. Instead, what I've done, and I want to show it to you, I mean, a little bit about the power of these tools. I can also formalize these kind of higher order functions, like, for example, the functor S and the functor R that map relations to state transformers and state transformers to relations. And then I can show these kind of injectivity, surjectivity, bijectivity conditions I was talking about. And then I can show all these order preservation properties. So R preserves the multiplications, and S preserves the multiplications in the other directions, and so on and so forth. And the proofs now become a little bit more complicated, but you can still get pretty far by just trying to do these proofs, right? And at the end, I just then introduce the star, and then I prove my interpretation statements. Anyway, I mean, it's sitting somewhere. Are there any proofs about Isabelle so far? About reasoning in these simple algebras and in these models? Yes?
You said that you're just a good user. Would there be can you foresee anything that would cause you to change from using Isabelle?
Yes, I'm changing from Isabelle at the moment. I mean, I wanted to do it for a couple of years, but I couldn't. One reason is because, I mean, in my mind, I'm more a mathematician than a computer scientist, maybe. And so I like the freedom that I get from, dependently typed provers to formalize mathematical statements where I feel really somehow limited in Isabelle. I'm glad that Andre is not here, because he would probably say, no, you can do everything in Isabelle. And one way or another, of course, you can. And so and there's another reason, and it's somehow a little bit sad reason. because all software tools that are produced in academia have life cycles, and there's always a danger that they come to an end when the people who have basically developed them retire, right? And Larry Paulson, the Cambridge guy who was basically the inventor of Isabelle, I think he's retired now already. He retired just now, I think. And Tobias Nipko in Germany, who has done most of the development in the last 10 years, because German professors can have these huge research groups, he will retire in the next couple of years. And the main developer is working as a hobbyist. He's not in academia. So it is, I don't know. Nobody knows what will happen with Isabelle in the next 5 or 10 years. Whereas, on the other hand, Coq is very stable because it's embedded into the French research system where people have these researcher positions and they can always, get new people contributing to the development. So it's very likely that Coq in one way or another will be around in 15 or 20 years. And Lean, it's just, receiving so much attention that it's also very likely that it will be around in a couple of years, right? So these are the questions that you also need to ask yourself. But nevertheless, I still believe if you're interested in verification and if Isabelle is maintained and if you care about this kind of proof automation and the ease of use, then Isabelle is a very, very good alternative.
Is Lean getting a lot of attention because, as you said, it's a new kid on the block, or does it have some redeeming new features?
Has some?
Redeeming new features that you couldn't have in Coq?
I'm not enough an expert. Do you know?
Well, its main selling point is that it combines dependent types like
exactly.
and cloud automation like in Isabelle. So
But the proof automation is not yet there.
yes.
It's not yet there.
You can automate stuff using the tactic language and clearly you can write your own information.
In Coq, actually, related automation to what you said is the type hierarchies that they're building, so that
Yeah,
you can
exactly.
make use of the same tree that you show, and if you have enough axioms proven, you
No, this you can do. Yeah.
So,
No, but I mean these kind of methods try and these integrated external tier improvers, SMT solvers, you don't have that.
what's your experience view? Because you show that you're staying first order for a long time, and then of course Sledgehammer and other tools
Yes.
to do it. But then at some point you switch to high order.
Yes.
Do you see a dramatic?
Of course. I mean, it's like for induction, it doesn't work anymore. I mean, it's somehow surprising. I call it shallow higher order theories. If I have just a set with a set comprehension where I have a quantified first order formula, then no problem. I mean, Isabelle knows how to basically flatten the set structure. If I have a shallow second order that I can somehow reduce to first order reasoning, then Isabelle will figure it out very quickly. The simplifiers of Isabelle also work for higher order logic. So they have what they call higher order pattern matching. And that works quite well. Even for, but there's no guarantee, and the tools are much less powerful than, of course, the first order tier improver. But so sometimes, I mean, I was in a situation where I had to assume the existence of a function, and nothing worked. And then, I simplified my problem as much as I could. And then suddenly a lemma, I could get an automated proof or something, and there appeared a lemma that was called choice. And then I figured out that I actually was using the axiom of choice, right? Because the axiom of choice is just like a swap of higher order quantifiers, if you think about it. It's some sort of higher order scolemization, if you know about these things. And of course, I mean, you can never prove such things automatically in first order logic in principle, right? And then you use Isabelle like you would use Coq or Lean. But as I said, I mean, for example, the relational model or things like that in Isabelle, the libraries are so good that Isabelle often picks up ways of simplifying things that are really surprising. What I do when I have these kind of, set structures, higher order things, I expand my definitions as much as I can. I call Isabelle simplifiers, and then I try basically to sledgehammer it away or something like that. And that is often quite effective.
Humans shouldn't be doing trivial stuff that will appear tomorrow in the neural network lecture. You don't want to do trivial sums by hand. You want SMT solvers to do this.
Yes, exactly. Yes. Well, no, you shouldn't. You shouldn't. But again, you know, I mean, you can write, for example, tactics in Isabelle. Let's say if you're working in this setting, unfold all the definitions that you have, simplify as much as you can, and then basically try to prove it, and that's how it would work. Yeah. But I mean, one of the nice things with Isabelle, I mean, I'm getting off topic, but maybe it doesn't matter, is that if you're building models of something, and you want to prototype with your models, and ideally, if you have algebra, because it's so simple, some sort of algebra, right? And then you have some axioms, for example, and then you want to have a minimal set of axioms, maybe, right? And then to prove that some axioms are redundant, it's very, very easy to do that with Isabelle, because if one axiom depends on another one, maybe you can prove it. If it's independent, you take it out of your axiom set, you add it as a lemma, and then you try to find a counterexample. If you find a counterexample, it's independent, right? Sometimes you prove things, you have set up an axiomatization, and you prove things, and then you realize at some point that the same proof patterns somehow appear over and over again, and then you think that something is wrong, and then you can hunt. You can try to pinpoint the mistake and go hunting with Isabelle. So last year or 2 years ago, I don't remember precisely, I was working on, let's say, strict higher categories, whatever they are, in Isabelle. And I copied axioms from a very famous textbook on category theory. And I could prove strange things. I realized, I proved everything I wanted. And then suddenly I realized, you know, I could not reconstruct the proofs by hand because strange things were going on. And then in these higher structures, you have these kind of source and target maps at different dimensions. And then I say, okay, let's assume it's like the source and the target in the graph, that the source equals the target. I could prove that. Then I have different layers of dimensions. Let's try to prove that the sources and the targets in different dimensions are the same. I could prove that. Let's prove that all the compositions that you have in your categories at different dimensions are the same. I could prove that too. It's what people call the Ekman-Hilton collapse, right? And without a theorem prover, I think I would not have found this mistake, right? I had this bug following the book, and it was only, they were not really precise about the definedness conditions in the categories, because that's what people often gloss over it. But if you just implement it naively, for example, in a theorem prover, you can make terrible mistakes. But on the other hand, the tools sometimes help you to pinpoint these mistakes and to avoid them and to repair your theories. I mean, for this, I mean, I think these things are really, really effective. But anyway, let's show you some more stuff. Yeah. So the next thing I have Kleene algebras with tests. Let's click. Okay. Well, okay. Yeah. This is my axiomatization of. Is this small now again, or is this a good size?
It's the same size.
Good size. Okay. Thank you. Yeah, so this is Kleene algebra with tests. You don't recognize it, right? When I had it on the slides, I said we have basically two sets. We have a set for Kleene algebra, we have a set for the Boolean algebra. The sets here are represented by types, but if you look at this map A test, you see that there's just one type floating around. So the problem is that in a type class, I have only one type parameter. If I wanted to have a Boolean algebra and a Kleene algebra, I would have to use two type parameters. Isabelle doesn't allow me that. It wouldn't be a problem in Lean or Coq. So what I do is ultimately I want to define a test function, which is this function tor here, which maps elements of a Kleene algebra into elements of a Kleene algebra, and which basically, so that the image of a tor, so tor of an element x is a test, which means I have to define axioms in such a way that I get a Boolean algebra of it. But I can't do it properly, right? Because I can't encode negation. So I need to define something that I call an antitest, which is a negated test. So that's what I do here. So I've got a function antitest, which maps basically an element to a test involving a negation somehow, with the hope that what I get out of it, of these axioms, will be a Boolean algebra on the image of alpha with regards to my carrier set or something like that, which is really contrived, right? But I mean, I've been working on these algebras for so many years. I mean, it's like a bus driver, right? You know how to drive your bus, and I can give such definitions and make them work. And then you start basically showing that this is actually a Kleene algebra with tests. You prove lots of little lemmas about it. And then you can basically show with a type definition, in some sense, I mean, I do not want to show you this in detail, but here I can basically show that the test algebra that I get, that I have somehow defined as this type, actually forms a Boolean algebra, right? So I can do that, and then I'm good. And then I can, prove some little properties in order to make it work like a Kleene algebra with tests. And then I can continue proving all these little lemmas and instantiation statements showing that my relations and state transformers actually form Kleene algebras with tests. But then coming back to your question, another way of doing this in Isabelle would be, instead of using a type class, a local as a specification mechanism. What a local is slightly obscure, but essentially it is basically in a set-based world. It's a context in which you can, again, do reasoning about structures. So here, what I do, I now have a Kleene algebra, and I take a Boolean algebra, which comes from Isabelle's main library, and I say a test is now a function that embeds an element of a Boolean algebra into a Kleene algebra, right? Which is a natural thing we do because we said texts are considered as programs, so I somehow need to embed them into the Kleene algebra. And then I add some properties telling Isabelle it's actually an embedding, which means an injective function that maps tests into programs. And then I can start proving properties that way, right? And I could actually also use locals to reason about Kleene algebras with tests. But then I leave my kind of type universe that I like, and I work in set theory. I mean, but people can do whatever they want. The user owns the means of production, right? That's the slogan. Okay, that's basically the mathematical components. The next thing I wanted to show you is propositional Hoare logic. And you remember, I mean, this is now in this kind of one-sorted Kleene algebra. This is the definition of the Hoare triple. I say the Hoare triple holds between precondition P, program X, and postcondition Q if the test P multiplied with the program X is below the program X multiplied with the test Q. So I just decorate all my tests with TORs to say that they are types. I mean, that's what I can do in this setting. Oh yeah, I've not shown, I've forgotten to show you, but I mean, there's not much to see. In Isabelle, obviously, you can also write down definitions. And so in Kleene algebra with tests, I can create this kind of syntax for while loops and if then else statements. And here I create syntax for the while loop with an invariant I. Yeah, and it's basically what I showed you on the slides. It's basically simply the while loop. And then I can start proving properties of Hoare triples. Yeah, so here's a very simple one. Let's try this. Come on, Isabelle.
So here, while Isabelle is thinking, what happens to the I on the right-hand side of that definition?
Huh?
So on the left-hand side, you've got while P invariant I do X.
Ah, it's just an annotation.
Okay.
So if I annotate a while loop with an invariant, it should not change the semantics of the while loop, right? Huh? It's just notation. It's boilerplate, but I use it, as I said, it triggers a different verification condition generation. It tells me just use the invariant in the proof. That's it, right? But again, so this kind of simple fact has been proved automatically by Isabelle. But if you want, you can also do these proofs explicitly. I don't know whether I show an example. You can basically do the proof on paper like I had on my slides, type it into Isabelle one by one using this ISA proof language, and then you can basically verify all these things. And now what I can do is I can basically tell Isabelle what, I can tell Isabelle about Hoare triples in the relational model, and I can define boilerplate to make our lives easier. So, for example, here, as you see, P and Q in the relational model, there would be sub-identity relations. But it's more convenient for us to use predicates instead. Yeah, so I have a predicate here, and I have another predicate here. And this bool, maps to bool, means basically that a predicate in Isabelle is a Boolean valued function. That's it, right? So the whole Hoare triple is a Boolean valued function and hence a predicate. So, and now I have these coercion functions, you could call them, and they are basically isomorphisms between predicates and sub-identity relations that I have programmed in Isabelle to make basically the conversion from these Hoare triples with predicates to Hoare triples with relations. Yeah? So there's some stuff that you need to do, but if you look at it, I mean, this component with propositional Hoare logic, and then the formalization of the things in the relational and the state transformer model is really very small. It's a very small component, so there's not much work going on. And in this component, I've also done my work both for the predicate transformers and for the relations. So now, for example, if I have a while loop with an invariant, I can design a lemma that tells me that that allows me to reason at the level of predicates, right? So, for example, I need to show that the precondition implies the invariant, but this is now logical. It's no longer relational, right? So P is a predicate, I is a predicate. The postcondition is implied by the invariant if the test fails. Again, I can do it at the level of predicate logic, which is great for Isabelle simplifiers. And then here, of course, I have the Hoare triple for the body of the while loop, which I need to manage by other means, right? And I can do the same thing when I have, for example, relational composition of programs, the Hoare rule for that. I can, decompose and then guarantee that at some level everything goes down to the level of predicates where Isabelle can then reason. So the next little component I have to write is the component for the program store. So I define this function update function, the delta that I had, which is basically this function FUP, FUP, whatever. And then I can derive these 5 or 6 lens laws, as I call them, right? So to reason algebraically about the program. And then after these couple of lemmas, I tell Isabelle what the store is. And in my case, so it's a map from variables to values. But in order to apply these laws here, I need to know when two variables are equal. So in Isabelle, I use the trick which comes from Mike Gordon, I think, that you just code them as strings. And then I can use Isabelle's string equality to make this decision. And then I introduce this auxiliary function set. And then I can already say what an assignment should look like, right? So that's the relational assignment, which maps me, uses set in this kind of graph-like statement. And then in the state transformer setting, where do I have my state transformers? Here. It's much nicer, right? So the eta is basically now applied with a function composition, but it means that the assignment is just my set wrapped into set braces, right? And that's it. And again, you see, it's very little work. If you know what you want to have with your store, Andrei Popescu could probably write it in, what do you think? 25 seconds, 30 seconds on a good day? I don't know. Yeah, okay, that's it. And then the last remaining bit that needs to be done is the derivation of the assignment laws, right? And now here, again, I use this encoding. I have predicates here and there, and I can boil everything down to predicate level reasoning, right? So the assignment law basically gives me an implication between two predicates where I apply my update function to the second predicates, and of course, I have to universally quantify over the states, which again makes that very applicable for Isabelle, because Isabelle is really great at reasoning in first-order logic. Then the second assignment law, and here is this Floyd law, which I was talking about, which allows you forward reasoning, and that's basically the derivation of it. It's a little bit of logic with some existential quantifiers and some kind of manipulations of these set functions. Well, and then the same thing in the state transformer semantics, and that's it. And after that, I introduce some syntactic sugar. I write basically precondition, program, post, Q, to make these Hoare triples more readable. And then I can basically start verifying things. And well, the first one is the first example I showed you, let's be bold. I use a very weak tactic from Isabelle, and Isabelle just managed, by simplification, to prove this little Hoare triple, right? If you want to do more complicated proofs, like, for example, that of integer division, so Eisbach, I don't want to see Eisbach here. So if you want to do integer division, which is slightly more complicated, you can write tactics in Isabelle, which pretty much automate everything that's going on for numbers. But if you do it step by step, you can basically just apply the rules. And then what you get is that step by step, the entire control structure of the program is plastered away. And at the end, you get rid of your assignments. And then the ultimate verification happens at the level of your data domain, right? So here I apply a sequential composition rule. So I get two basically proofs for the components. Then I apply a rule to the while loop, which blasts away the while loop of my program. Then I get 4 proof obligations. Then I have a couple you need to check now. What is it here? I'm in the relational model. Here's another sequential composition. And here's one. And I work my way up. So this is basically the first. Basically, if I descend here, I go up from the postconditions. So basically, I start working on the postcondition with the first goal, and then I go closer to the preconditions with the remaining proof goals. And then here, if I do this sequential composition application, you see then this goes away. Then I have a statement which only has an assignment here, so I can apply an assignment law. So you see I've killed the first proof obligation. Then I simplify as much as I can, and whoops, suddenly almost nothing is left. But I've got another sequential composition here. So now I'm dealing with basically the initialization block and apply my sequential composition. I have one rule. I do the first assignment. I'm left with one assignment. I simplify it by substitution, and then I'm done, right? And that's it. Yeah. So this is basically how you can step by step verify your programs in this little tool. Everything is semantic, right? So there was no program syntax. It's a shallow embedding. I'm using Isabelle's functions and relations. I don't have to define my own types. And all that is basically for educational purposes, right? It's not really a tool that you would sell to the industry. But of course, if you want to have program syntax, you can add your favorite program syntax. If you want to automate this further, you can do that by writing lots of tactics. And that's what people are doing. And in particular, with Isabelle, as some of you might know, they have already verified quite impressive pieces of software. So like, for example, this SL4 kernel verification. And of course, they use methods much more sophisticated than this one. But if you boil everything down to the bare bones, what you are doing in the most simple setting, based on a Hoare logic, it's probably very similar to what you've seen here, right? So just to wrap up, what I've shown you is this kind of algebraic approach. And I said the algebraic approach is nice because you can prove so many properties automatically. And then I showed you in Isabelle how that actually works in practice. And the benefit of the algebra is really, if you try yourself, that most of these Hoare logic rules, you can either prove directly, automatically, using try, or by just figuring out how you would do it in algebra, and then translate it step by step. It's all within first order, so that means really these automated techniques, they work. And then you need to write a little bit of boilerplate code. But as I said, it's maybe 10 pages if you print it out, that use these mathematical components and translate them into proper verification components. And you need to know some tricks to assemble things in the right way to make life easy for Isabelle. But then you do not even have to write any kind of functions for verification condition generation. So the way the rules are set up, it goes more or less by simplification, except for the while laws. And Yeah, and then the really tough stuff of program verification, as we all know, doesn't happen at the level of the program structure, right? So, in this sense, all I showed you was just an exercise in triviality. I mean, so Hoare logic gets rid of the trivial stuff of program verification, and at the end of the day, you need to reason about data structures, data types, and stuff like that at the data level, complicated objects at the data level, and that's what makes verification hard. But this is where I stop. I do not want to show you any hard stuff anymore. So thanks for coming here. Thanks for your attention.
So any questions for Georg? I think you will be here with us until tomorrow evening?
No. I unfortunately have to leave tomorrow morning.
Tomorrow morning, okay. So
But I'm here the whole day. I'm here the whole day.
during
Yeah.
lunch conversation. But are
Yeah,
there
yeah.
any questions specifically on the show today?
I have one, but I think it might be more appropriate for just about the reason.
I don't take. I mean, we have this kind of code of conduct, right, which does not allow me to take any inappropriate questions.
But I was just wondering if we have the time, if not, don't worry, why you particularly prefer, you mentioned you don't really like state transformers generally, and
No.
generally.
I said I like state transformers a lot. I said I do not like Hoare logic so much, right? Because well, I know many people are working on, but predicate transformers are much more powerful. And in every predicate transformer semantics, you can derive the rules of Hoare logic, right? So if you start with predicate transformers and then you suddenly start, you have this kind of urge that you need a Hoare logic, you can just derive the rules quickly and then work that way. Yeah. I mean, just as an example. So, for example, if I have straight line programs, most of the programs that I worked with in Isabelle, I can just simplify to the data level, right? Because all you do is you calculate basically your weakest liberal preconditions, which gives you basically precisely the effect that an assignment has on the postcondition as the precondition. And then you just propagate that through, and that's all. The only thing where that breaks is where you need to reason about loops with invariance. With Hoare logic, you always have this problem, in principle, you could be stopped by the proof automation when you separate a sequential composition and you have to somehow get the intermediate assertion. Why it works in my Isabelle theories, that's really a question over lunch. But you need to do some work to get there. And if you think in terms of computer science, programs for me are semantic objects and as denotational semantics, right? And I want to reason about them in the way mathematicians would reason about functions or about relations. Why would I want to use a logic to do that, right? I want to do it by computing basically the values as they are propagated through programs. And I think in a predicate transformer semantics, I can see that much more clearly.